আজকে সারাদিনের আছে 200 স্লাইড।
Just 2 minutes delay, I guess it's fine. So today we are mostly going to talk about hardware Trojan, and then in the second half how we'll basically detect them with different technique, including AI. Sir.
Is it ready? Good morning. Today we are going to talk about hardware Trojans, and here is a rough outline. First I am going to talk about how to design them, what they are. We will delve into the details, so that whether you want to work in the designing of hardware Trojan or detecting hardware Trojan, you will be able to do that. And when we talk about detection in the subsequent lectures, we will primarily focus on different techniques, and many techniques I talk about, all of them can be used as an AI metric, but I would specifically talk about how zero shot learning, explainable AI as well as reinforcement learning can be used for detecting Trojans. And then finally, I will talk about, now that attackers know you are using AI for detecting Trojans, so then how would they attack your AI model itself, and we will talk about AI Trojan, how would a Trojan look like in the AI model itself and how do you mitigate. So, to set the context where hardware Trojans comes from, we need to talk about the supply chain vulnerability. There are many places they can come in, and supply chain vulnerability, the starting point itself is the integrated circuits or hardware is very complex, systems are very complex. In early days, even 20-30 years ago, companies were able to design everything on their in house, but because of the complexity, there is not a single company in the world they can claim they design everything in house and they integrate everything in house. So, maybe they are taking processor from company ARM, digital signal processor from Texas Instruments, different analog component from analog devices. So, they are buying components from different companies. It is not just the component, the components are getting through compilation, synthesis, testing, fabrication. So, that is basically causing all these problems. So, what I did for one of my sponsors, and I am not allowed to tell the name, I took the devices and trying to figure out where the pieces came from. So, this is one of the router, and when you think of router, do not underestimate it, this is a multi-million dollar router which most universities or different countries basically buy the route to route different types of traffic at institute scale or at the country scale. And those components when I plotted, so basically as you can see it is all across the globe. Now, you might say, well, I do not see anything in South America, Africa, Australia, but it just for that device, that SoC, it did not happen. You take another SoC, you will find that. But the funny part is, I mean most interesting part is actually what you see, that is a static view of the story. In fact, maybe some component got designed in San Jose or Santa Clara, it might have traveled to India for kind of testing, scan chain insertions and so on and so forth, might have gone to Europe for integration, might have gone to Taiwan for fabrication, might have gone back to USA for final assembly, and it might have made many trips around the globe, crossing different hands and different companies, and that is where the sources of vulnerabilities are. When you keep your secure document inside your room, inside the locker, that you know when you want to access it you have. If that is changing hands, one of your friend is picking it up from the postal department, then they are dropping in their friend's house, their friend's house has tiny kids roaming around and tearing off things, the reliability of your document would be in question. Until you see it and know it is in single piece, only then you know. And who are these people? So, always we do not have to assume that attacker basically meaning all bad or evil people. It is a combination of them. Some employee could be a state level spy, country level spy, they are trying to doing spying activity. So, exactly whatever Israel did on the pager attack. So, it could be a state element, they have a vested interest, they are willing to spend as much money as needed, then you can't do anything. Even it could be a disgruntled employee who did not get promoted or got fired, and that is why when they fire an employee they immediately lock everything. So, it could be a combination of all of them. Even it could be somebody not really malicious. So, like the way when we talked about finite state machine vulnerability, we talked about the synthesis tool generated something which happens to be vulnerable, and Dr. Karfa spent a day of lecture on talking about how do you mitigate, mask and blind and all that stuff. So, even compilation or synthesis tool introduces vulnerabilities which later somebody can exploit, later meaning when the device is in deployment, is in use, somebody can mount a vulnerability, mount an attack because this has a vulnerability. So, the supply chain, and in fact, if you think about it, when I talk about security, I forgot to mention security is not about the way you think about security. In fact, if you talk to the Ministry of India, they will talk about food security. Do we have enough cultivation, enough grain in store? If it does not rain for certain amount of months or years, are we okay? Do we have some kind of conflict with other countries in terms of import and export? Do we get enough grains that our people in India need? So, that is also food security. In fact, many of the rare earth materials in specific countries, if they are hostile to you, they are not going to give you those rare earth material, then you cannot design chips. If you cannot design chips, then you cannot have cars, or cars going to be extremely expensive. So, that is basically going to be a security problem, national security problem. So, sometimes security in the sense we think, oh, somebody stole my iPhone, somebody hacked my bank account, that is really microscopic problem. It may be a huge problem, somebody dies in my house, it is a disaster for me and my family, but for rest of the crores of people it really does not matter. They do not cry for somebody dying at my house. Same analogy, when your bank account gets robbed, it is big deal for you, but not as a society, not for a country. But if there is a national level attack, whether on the food security, national security or any of those, then that is also a security problem. And the vulnerability, supply chain vulnerability, if you recall, when there was a boat jam in one of the traffic lane, and then things were not moving, all these big ships are not moving, suddenly every prices have gone up. During COVID time there was that supply chain problem. So, that supply chain security problem and this problem is same, it is just that it is a microscopic. We are talking about components inside a system, software, hardware, and when other people talk about supply chain security, whether food, grain, car, rare earth material, fuel, whatever supply, that is also a supply chain security problem. Any question on this idea that this is actually changing so many hands? Now, at some point you might be thinking, wait a minute, and throughout this discussion I would be using the term potentially untrusted. TSMC is a multi-billion trillion dollar company. Why would they insert Trojan in your device and tarnish their reputation? They won't. They won't. They would be interested in buying fabs from Intel and all that. They want to expand. They want to expand their portfolio. But the thing is, it is not necessarily any company knowingly doing it. In fact, my first company was in Texas Instrument. I got salary hike. I do not remember 500 rupees, because my salary was 7,000 rupees, it is 500, 200 could be. I was so happy jumping around, I asked my cube mate, how much is your salary hike? After 1 year that guy said, I am not an employee in this company. Now, this is a contractor from InterSystems, I am not even remotely suggesting this guy has anything negative to do with it, but I am saying I am sitting with somebody for 1 year in my cubicle and I do not know that person is not even an employee of my company. So, you could imagine all these people working in different companies and the things changing hand, you cannot just trust. If right hand cannot trust the left hand, then you could imagine this whole trust business that you can assume safely, oh, this is from a branded company, therefore, it should be reliable. We cannot do that. You have to do your legitimate thinking and verification. And so, is it clear that this supply chain or this huge global supply chain is essentially the cause of concern for security? If there is a single room, single company, everything developing, that would be extremely reliable. Now, it is not, should not be a surprise, that is why we see so many types of problem, and in this today's lecture I am primarily focusing on problem at the design stage, little bit of fabrication, but what I am not going to talk about, that is 90% of the story I am not going to talk about, which is all the way from assembly, distribution, lifetime, end of life. Let me talk about end of life, so that you get an idea. So, many rich countries, what they do, they send their garbage to the developing countries. I did not wanted to say poor countries. So, they send their garbage and they take all the good stuff from there. A ship full of garbage comes in, and that garbage meaning old computer and old car and all that stuff, that goes to those countries, and from those countries all the good stuff goes back in the ship, and everybody thinks they are the winner, and you know who the real winner is. But what happened over a period of time, the dumping ground, somebody figured out about 30-40 years ago that in the computer or car whose lifetime has expired, some of the chips are still working. Original intent was you take the chip, melt it out, there is a minuscule gold, lot of rare earth material, extract it and then sell it, and that is enough money to do this recycling business. But some smart dude figured out that those chips actually work. Then they started coloring and painting, and it is a $1 trillion business actually, this recycling chips, and that creates significant security vulnerability. You buy a new stuff and it does not work, then you know it is either pirated or one of those recycled materials. So, therefore, vulnerability is throughout the stuff, but in this lecture I will primarily focus on software, hardware, code level, programming, design level, little bit on the fabrication level, but I am not going to cover rest of that stuff. And Trojan is just a name, it is basically somebody maliciously implanted something, right. And in fact, people do that all the time. If your kid is not listening to you, that basically means somebody implanted something on their head, you should not listen. And if your parents say something, call 911 and your parents will go to jail. So, pretty much that has got implanted. So, Trojan and all that stuff is basically malicious implants. So, there are, as I say, there are big spectrum, there are piracy issue, reverse engineering. From the design somebody is trying to figure out what is your intellectual property. You and your team spend millions of dollars to do the research to develop the product, they will just photocopy, right. But today I am going to just focus on malicious modification, and specific instance of malicious modification is hardware Trojan. So, before I go, let me be a devil's advocate. Almost half of the researchers do not believe Trojan exists, they do not, other half do, and even the half do, about 90% of them are not interested in working in Trojan, right. But in early 2007, DARPA, the US defense agency, invested hundreds of millions of dollars in this program. So, that is at the time I got convinced that there is something military cannot tell us, otherwise why would they invest so much of money. There are something, and of course, later we knew we are not allowed to tell. Now, you see all these examples of pager attack and what not, and those of you do not know the pager attack, you develop a pager somewhere, and in the supply chain when postal departments are sending it, open that, put your trigger in, and then when all these military people of your opponent country are using pager or with them, you just blow them up so that they can die, you can do the damage, but it is basically nothing but Trojan. So, what I am going to do, I am going to talk about anything you design, although I am going to talk about today hardware Trojan, there are many other attack models. Anything you attack, these are the 3-4 core components you want to talk about. What is the coverage metric? What is the metric? Because in functional domain is very well defined. What is the metric? Statement coverage, line coverage, branch coverage and all that stuff. In security domain things are evolving, even today it is evolving. I still want to talk about little bit about metric. What is the metric? And once you have the metric, then you want to talk about what are the benchmarks. If you develop a Trojan detection tool, I develop a Trojan detection tool, how do we compare? Because I will run on my design, you will run on your design, and that used to be the case even normal world. Not normal world as in Intel developing processor, ARM developing, AMD developing, everybody is saying mine is better than theirs, because they are running their own designs. Then came the consortium about 20 years ago called SPEC. So, people from different companies came together and tried to decide, okay, these are the 10, 20 benchmarks that every processor company should run. Now, it is very interesting game actually. When Intel wanted to push one of their design in very forcefully, other people will know. So, they will try to push it back. So, if you are doing a horse racing and if the person who reaches last wins, then you cannot drive your own horse, you have to jump to other person's horse, try to race it as fast as possible to make that person lose. And it's unless you sit in that table, you do not know how it goes. If you wanted to push your benchmark, you try to pretend you do not want that to happen. Even the same analogy, this tug of war, oh, I do not like this benchmark, this is unfair, then other people will think, oh, this is probably a disadvantage for this company, let us push it in, and that is exactly what you wanted. So, static and dynamic benchmarks I will talk about, then I will talk about something little more interesting, which is how do you discourage attacker from inserting Trojans in a design. So, which is rareness reduction. So, you know what Trojan is. So, key idea is not, it is not important what the story is, key idea is how can I hide in such a manner so that nobody else can identify it, but I can take advantage of it when I want to take the advantage. That is the key idea of Trojan. And before I talk about Trojan, the threat model is important. You hide in rare signal, rare variable. So, I wanted to give you an idea what that does rare mean. We can compute rare in two ways. One is statically, if I give you a design, you can just walk through, find out what is rare, or dynamically through simulation. Whichever way you do, I will walk you through. So, if this is an AND gate, this is the absolute front input of a chip or your program, first time it is entering. So, we can safely assume the probability of 0 and 1, or this is 1, this is 0 is 50-50. That is how we are going to give the input, right, you can control that. 50% of the time that value is 0, 50% of 1, but once it goes through the AND gate, if you remember the truth table, output becomes 0 3 times and output becomes 1 only once under 4 possible combination. So, it should not be surprised the 0 probability is 0.75 and 1 probability is 0.25. So, similarly, if you have multiple layer, I am not going to show you the math, but this is another layer of AND gate, this is what will happen. The interesting part to observe, the probability of 1 was 0.5 here, it became 0.25, it became 0.125, it is getting reduced. So, if you have a significant layer of AND gates, the probability of that value being 1, if it is an AND series, is going to go down significantly. So, that makes it rare. And so, typically there are two terminology people use, it is not important. Given a variable, what is its rarest of number. So, for example, if we are interested in x, should I take it as a rare signal if I am an attacker to hide behind it? Is it rare enough? Whose is the rare one? So, basically under value 1, x equal to 1, that has a 0.125 probability of being 1. Is it rare enough? That is different. In the whole circuit, what is the rarest value? That is in this example, it still happens to be the same. Another design, if x I wanted, the rarest value is 0, x equal to 0, that is the rarest value. What is the rarest story in the whole circuit? It is this one. I did not give a name for this variable, but whatever this variable is under 1, 0.25 is the rarest value in the circuit, and for a specific signal this is the rarest value. Is these two concepts clear? What is the rarest value of a signal or of the whole design? Of course, one signal is not important, eventually we will consider many, but I want to have a feeling that you know what rare means. Yes, please. You can say, I can repeat.
Sir, why the probability gets reduced in AND gate and probability gets increased in OR gate?
Oh, because that's the truth table, right? When you have A and B and 0 1 1 0, what am I doing, 0 0 0 0 1 1 0 and 1 1, if you look at the values, the way it produces 0 0 0 and 1. So, probability of 1, it is 1 in 4 in case of AND gate, but in case of OR gate probability of 1 is 3. So, that is why probability of 1 increases, another one decreases. Even here you see the OR gate, this one is decreasing, but 1 is increasing. Any other questions? Okay. So, all right. So, now that we know what rareness means, how we want to hide, how would you do in a dynamic environment? You take the design, simulate it, apply random inputs, millions, more you give it is more accurate. If you run 5 or 10, that is not so accurate. If you run millions of test cases, then for every signal you count how many times it is 0, how many times it becomes 1, and once you have that, then you compute the percentage. And but the thing is, what is rare, what is not rare, a designer has to choose what do you call rare, right. So, for example, if I go back to the previous signal x, and if it is 0 for 90% of the time, then that means it is 1 for 10% of the time, right. So, that is basically, and if that design we say rareness threshold is 0.1, so then we select that signal, we as an attacker select that signal as a rare. But somebody may say, yeah, 10% is not rare, we really want something. So, 0.1 is 10%, we really need somebody 0.01, 1%, somebody say even 1% is not rare. Now, can anybody tell me why are you so, as an attacker, why am I so much after rare signal? How is it helping me hide? Here at least I know this is a broad daylight, this is visible, here there is darkness, I can hide there. But here what is the hiding? You can still see the circuit, you can print it. Remember, we are still talking design stage, not in fabrication stage. What is the hiding business with rare? How does that connected?
Because the vulnerability will be observed only at that specific signal will be the trigger.
Right. So, the thing is, one thing I did not say is that if you have a rare, so two things, if you have a design, assumption is we won't, during simulation we won't be able to run all possible inputs. If we can run all possible inputs, attacker has no place to hide. No matter how rare it is, if you run all possible signal, at some point that signal would be activated or that trigger would be activated, and if it is a functional Trojan which changes the functionality of the device, changes a green light to a red light, then if I have a golden design, I am comparing the output would be different, I will be able to catch it. But assumption is number of input is so much, in a typical SOC it is about 300 bits, about 2 to the power 300, we could not try those many inputs in lifetime of the universe. So, if we cannot run those, so that means when you run any random input, the signals that are non rare, they will be activated, and the probability of signal that is rare, the activation probability is extremely low. Rarest the signal, and remember how did we compute, that is how we computed who is becoming 1 how many times. And in fact, most designs, even if you run million, many signal in the range of 10 to 100 signal, activation of one value would be 0, it will never be activated. So, maybe the rare of 1 you will never find 1, the way circuit is designed, about 10 to 100 in a million gate design, they will never be activated, right. And only way you guarantee that by running all possible input. So, this hiding business, rareness business is related to this, because a designer or verification engineer will not be able to run all possible inputs, and rare signal only gets activated in extremely rare scenario, and attacker knows that scenario. Which input would activate it, attacker knows that, and that is where attacker hides. Any question? So, that is why we are computing rareness, the signal, and the key idea is if I insert a Trojan during normal verification time in the company, nobody will be able to detect it. If your company run 1 trillion test cases, that should not be able to activate. And to make it even more interesting, what designers do is even more smart, which is they do not take one rare signal, they take n of them. In this example, I am taking one rare signal, let us say this is 0.1 probability, 10%, remember 10% is not really rare in standard world definition, this is 0.1. I want to see hand, how many can tell me what is the probability of this output? If the input is 0.1, 0.1, what is the probability of this output for x equal to for value 1, if this variable is x? You already saw the static computation, right. This is dependent or independent probability. First, this is dependent probability. Even if you did not know this gate, if you did not know this gate, it is still 0.1 times 0.1. So, it is going to be 0.01, but if you know this is AND gate, then the truth table whatever you saw, right, 0.5 becomes 0.25, but typically it is 0.1, 0.1. So, it is like it is going to be, if you do not know this, then it is going to be about 0.01, simple multiplication, that is not accurate. Now that you know AND gate, you have to do the truth table thing. So, basically this is for 2 input, if you make 3 input, then it becomes 0.001. 4 input, it becomes 0.00001, that probability become like ridiculously small for anybody to ever activate it. So, any number, we did some research here, any number greater than any, if you create a something greater than about 10 or 12 I believe, then it is basically theoretically impossible even to activate it. If the probability is 1 over 2 to the power 12. Now, you would argue who would insert such a big AND gate? Now, do I find so many rare signal? Yes, in a million gate design you will find so many rare signal, but who will put a AND gate with like 12 inputs? Nobody will, because then you can just see the design and you can figure out. They will do a chain of that and they will hide that chain. So, chain as in, if you want to do a 3 input AND gate, you will do this. You still have 3 input AND gate, but you will not create one big AND gate. In fact, most of the synthesis library you do not have 8 input 16 input AND gates, you still have to choose from 2 input or 3 input AND gates that they have in the library, but it is basically a chain. So, in early days research people used to put chain, then the defense mechanism was if there is a AND chain, that does not look like a normal design, let us get rid of that elimination. Then people realize, they try to hide it, but no matter what it is the key idea clear that attacker's job is to make this trigger condition really extremely rare. So, Trojan has 2 portions, one is trigger which I was talking all along, now I am going to talk about payload. Trigger is like a trigger of a switch that Israel did, press the button whenever they are unhappy with that, and that is it, that blew those pagers, that is the trigger. Now, blowing the pager, killing the people, that is the payload. Here in this example, just by looking at the circuit, can anybody tell me what is the payload here, what is it trying to achieve? Anybody please, just turn on your mic and please say it. What is the payload here? What is trying to achieve here? If this trigger gets activated, becomes 1, what does it do? It flips this signal. So, this is your design. So, which part is design? All of this is your design. Think of millions of gates. You only added these 2 extra gate, one trigger gate, one payload gate, XOR gate. In this particular design, trigger you understood, right, extremely rigor. When it becomes 1, you mark it 1, okay. Attacker is able to find primary inputs attacker knows the primary input, that will make this line 1. When it becomes 1, if this line is 0, what would be the output? Okay. Let us take a different color. If this line is 1, what would be the output? So, do you see, if this is 0, it becomes 1, if this is 1, it becomes 0, that means it flips the value. So, if traffic light is supposed to be green on one side, you make it red, supposed to be red, you make it green, you change the functionality. So, this is a very simple Trojan. This is also known as combinational Trojan, because it relies on combinational logic, and the idea is you create an extremely rare trigger condition, an attacker can relax and sit, and whenever wants to trigger the switch, it would trigger, and what would it do? It would change the functionality. For information leakage, it may drive your car to the ditch, it knows when exactly you are on top of a bridge or something, that is exactly when it will malfunction, and it will take a left turn, and it will go down the drain or river or whatever the objective. It basically flips the story. Let us say you are running in a user mode, privilege mode is 0, super user mode is 0, and this will change that super user bit to 1. This is not a laser fault injection attack. In laser fault injection attack, you need to know, you need to be in the vicinity, point to the chip, you have to know where the register is. Here you earlier embedded it, and whenever I feel like I will attack you. Maybe today you are friendly to me, tomorrow you are not, so I will basically attack on you. So, most of the attackers, they basically implant things on everywhere. They may not use them in their lifetime, but if needed they will. This is an exploitation technique. Any question? So, this is the key idea. Now, we will build on top of it. Yes, please.
How the rare condition happens? Someone need to provide some kind of stimulus input, then only rare condition. Who will provide?
Rare condition happens, meaning who makes it 1? See, the input, a specific input will make it 1.
But input need to come from somewhere else, then only attacker need to come.
Right. So, the triggering mechanism can happen in different ways. If you think of a pager attack, so these have transmission devices, they have reception device, very tiny, so that Israel military can sit in the inside Israel, trigger that, and that would receive in Syria in front. So, that whether it is a wireless, where, near, far, that is an independent discussion. You have to have that mechanism in built, like the kill switch example. A country won the war by destroying the planes in the sky. So, kill switch mechanism was designed for a legitimate purpose, that if it is in enemy hand, you destroy itself. So, that enemy cannot figure out how your airplanes work. But the other country basically put a Trojan in the kill switch, so that it can fake and tell the system I am in enemy hand. So, that is again wirelessly transmitted signal. So, these input values could be wirelessly, could be there, near, it could be your computer, I just press Control Shift something, and it basically destroys your computer. I may have access, may not have access, but that the idea is what value would create that trigger condition, that attacker knows. How you deploy that input, that is a different story. Any other questions? Yes, please. None of them? Okay, go ahead, I will repeat the question.
Okay, sir. So, this thing you are talking about in design phase.
This I am talking about in design phase, but this will work even. So, the question is whether it is in the design phase. I am talking in the design phase, but this will work in any phase. Think about a fabricated circuit or a computer. If you know in computer which keys to enter to apply to create a trigger, you can just do those keystrokes that would create certain set of values, and then whatever effect it is going to print something on screen. My girlfriend's name would print on the screen, that is what will happen. So, what is the payload, what is the trigger, whether it is fabricated, non-fabricated, it is different, but it has to be embedded in the design. Again, it could be in the design stage, it could be in the fabrication stage, it could be in the assembly stage. I will show those Trojans also. Somebody putting chips together, Trojan is not inside the chip, but when you are putting different chips, memory and software, at that stage you put in, right. And most of the attacks are when they are collaborative attack. Software will help hardware, who will help somebody, and then they will get data from somewhere, they will forward data to somewhere else. there are a lot of interesting ones. Right. Any other questions?
Sir, but how as an attacker I can get information about all the rear signals happening here? Because rear signals and where it is in designing phase or fabrication phase, it should come from an insider attacker. But how an outsider attacker I can analyze all the things and get the information about what input will create what output?
Yeah.
How?
So, very interesting question. So, two assumptions here. Assumption is attacker knows everything about your design. Attacker has access. If attacker does not have access, how on earth they are able to put it in, connect signals and all that stuff. So, attacker knows your circuit, attacker knows who the rare signals are, and attacker knows which one to make one. So, that is the first point. Second point is how does attacker know what value it will, because attacker knows this needs to be one, there is a technique called ATPG, I will speak in like half an hour, 1 hour later. That ATPG technique you can go back from here and automatic test pattern generation, you can find the pattern. So, attacker has done that in house. Attacker exactly know the trigger I am trying to make, what is the exact input that would create that trigger, because otherwise all the effort of the attacker is useless. Attacker knows that. You and I do not know if we are the verification engineer, because we do not know if there is a Trojan, number one, and even if there, unless we try all possible combinations, that line will not get activated. The probability of that line getting activated is extremely rare, that is why we call it a rare trigger. Any other questions?
One more. Last
Go
one.
ahead.
Okay, so you are talking about rear signals. So they are the primary cause of zero-day exploit, yes or no?
0-day exploit, not necessarily. From a designer perspective, it could be 0-day exploit. From attacker's perspective, or if you believe it is a threat model of rare, as I go along, threat model may not be rare. It just it makes it simple to discuss. So basically, it is not that you do not know, you know. So, you do not know malware would be installed in your computer or ransomware, you do, but it is just that you are not able to protect it, right. Okay. So, now let us zoom into if you are a designer, how would you design for a typical combinational Trojan. It could be your C Java program, it could be VHDL Verilog code. The key idea is you look at the variable, figure out who is rare under what value, and remember we talked about binary signal. It could be a variable in your C program with 32-bit number, you have 2 to the power 32 possible values. For one of those values it is extremely rare, and which has a higher likelihood, because each of the values probability is, even if it is a uniform distribution, 1 over 2 to the power 32. So, a very specific pattern of 32 value, if you use that, even in this one it is like extremely rare. So, this if you are a computer science or programmer, this is kind of the view. If you are a kind of from computer engineering EC, then the view would be, well, I find who is the rare signal, I create a trigger, then create a payload, and that is basically the view, right, simplistic view. Any question on combinational Trojan or how you would design a combinational Trojan? Let us look into the sequential Trojan. Sequential Trojan is much more powerful from attacker side, much more difficult for the verifications person side. So, you have a finite state machine with lot of states and transitions, and then attacker is going to do the same thing, the way they did rare value variable analysis. They will be running this with millions of tests and trying to figure out which transition is rare, and most of the time a vast majority of transitions are rare, because they are never activated. So, then who is rare, and as you realize, if there is a if statement which is not activated, anything inside that if there is another if inside, that would also not get activated. Anytime rareness hits, anything in that subtree, everybody is rare. So, if you have a if statement, for example, so if you have a if and then inside a very rare condition, and inside that there is another if this turns out to be rare, and most of the time in analysis rare basically means it never got activated, or one of the specific path. If so, for example, if I draw pictorially, this is a if else, then this is another if, there is else. So, you already have 4 possible paths here, right. One, I do not know 4 or 3. So, basically maybe this particular path is kind of rare, it did not get activated. So, that means a Trojan can easily hide somewhere here, somewhere there. So, that is basically the key idea, but nonetheless so, when you think of sequential logic, think of branch statements, for loop, any kind of conditional view, and if you want to look from a computer engineering perspective, then think of a counter and a specific value of that counter is what causes the trigger condition, but your payload is still similar. Now, I am still using XOR gate because I am assuming payload is functional alteration, functional change, you just flip the decision, but which count, which transition, that is basically a counter. For a specific value of that count you trigger. If counter is controlled by a clock, we call it synchronous counter. If counter is controlled by some asynchronous variable, we call it asynchronous counter. And this one I said maybe I as a attacker did not have access to when the processor got designed or memory got designed, but I have access to, I am a system integrator side. Let us say I am working in Apple or Samsung or Sony, Toshiba, Hitachi, all these big systems companies, then I am sitting there, then I can again I still have to know a lot. I have to know that when computation is going on, if certain information floating on the bus that indicates, then at that point memory would have the key, unencrypted. So, that is important. So, this is memory and we have the key at that point unencrypted. So, then what I can do, when certain information is here, I get to hear that. So, that is my trigger, a specific value here is kind of a trigger, and then I am going to either modify certain value in memory. In this particular example, I will try to read it and maybe wirelessly transmit, send it to another malicious software running, that is a different story. So, how do I trigger and how, when I extract the value, whom do I hand it over, that is kind of a difference. The spying activity, spy network, all that stuff you have to worry about. So, this is kind of system level Trojan, and there is a lot of work on PCB level Trojan, and there are many examples of that. Any question on system level Trojan? If you view this as an integrated circuit, then this is also not system level Trojan, bunch of components and you are putting your trigger and payload somewhere. So, the idea of trigger and payload remains the same. Now, we designed a tons of Trojans, and Trust Hub, when you have a computer, if you log into trusthub.org, we put all of those Trojans there, different types. Combinational trigger, I kind of talked about a very simple one, but if I am an attacker, if I know you are detecting based on rare, I would combine some rare and non-rare. Of course, mathematics says it is a bad idea, because probability of detection if you combine rare and non-rare is basically detection is higher, but no matter what it is, if I know you are doing something, I want to evade that. If I know you are looking at the bottom of the table, then I will put the camera in your hotel room right there, you will not even suspect. Nice flower vase and nice stuff, camera is embedded there, you will not be looking for it there, right.
Excuse me.
Yes, please.
One doubt, sir. Like we have spoken about the triggers, which can be combinational or sequential circuits, but in both they trigger a particular payload. So the malicious circuit is the payload itself, and that has to be integrated within the hardware itself, or can it be a software-based payload, which is the malicious part?
Right, interesting question. So, the question is trigger could be combinational and sequential, but the payload, should it be integrated in the design itself or it can work with somebody else. In fact, trigger and payload does not even have to be physically there. If you are collaborating with another entity, trigger could come from software. A software will tell you, okay, now start recording, then software is the trigger. How the software decided that on the earth, that is different. Same thing about payload. Payload is about what do I, at certain opportune moment, what do I do? Do I leak some information, change some information, there are few choices, and once I decide that, do I store it in a buffer? Remember the example of Xerox 941, the US spy was stealing from Russian consulate. So, basically do I store in an internal buffer, somebody else will come and take it out, or should we just transmit as a signal, somebody sitting in the next room would be able to absorb it, or should I just change the traffic light from red to green, so that some accident, some people die, that is all my objective. So, trigger and payload, it does not even have to be integrated right then and there, it could be in any manner. The easiest examples are, they are all there, few circuits, but I want to dispel your notion, oh I can see my circuit, you can't see your circuit, because, and some people tell me, oh why do not I do just diff of 2 circuits, because you have to understand that when you want to do diff, it is not just the 2 extra gate. If you had the golden design somewhere, somebody came in and added 2 extra gates, you could do the diff, but in general what happens when hands are changing, they are doing something, compilation, transformation, power, dynamic power management logic. So, they are adding lot of stuff, in addition to this got added. So, that is why diff will not work, eyeballing will not work, it is a millions of lines of code, and fabrication time people think, well I will run 2 circuits and then I will see if somebody is consuming more power. First of all, you do not have 2 circuits, you have only one, and that is why when I talk about AI, we will talk about golden free. Most of the golden free Trojan detection methods are AI based methods. You have only one design, there is no golden design with whom you can compare, number 1. Number 2 is that the notion of process variation, because each of the gate, the amount of power they consume or exact area, it is not identical. If you create millions of AND gate, same fabrication technology, same day, same time, they will have minor, very small minor variation, but if you multiply that by million, then you are looking at a number, looking at a, people say 2 to I do not know, people say 10-12%, even if I do not go for 2, I go for 1% variation in time, power, area, 1% of a million is huge, in the order of thousands of, you could potentially add thousands of gates, still you will not be detected in a chip, in the power and all that. In fact, most Trojans, although I am showing a silly example of 2 gates, it is in the order of 10, 5, 10, 100. So, it is not going to go in the ballpark of 1000, you will not be able to detect in any manner. Does that answer your question? Okay, so, there are many, I am not going to go through laundry list. So, rare we talked about, rare we talked about a lot, and what did I do? Rare we talked. Now, the rare and non-rare combination is possible, then sequential at the programming level it could be rare branches, at finite state machine rare FSM states or rare transition, synchronous we said when it is incremented by a clock, asynchronous when incremented by some event, think of a variable, input variable or something else. It could be a combination of both synchronous, asynchronous, and it could be a sequence of rare event. Think of one counter, when it becomes 5, then starts incrementing another counter, when they becomes 10, it could be a sequence of event. In programming level it could be nested rare statement. Remember, attacker might not have added nested rare statement, you might have had nested rare statement right there, attacker decided to embed there. And then there could be hybrid. Let me show you an hybrid example. So, this is your design, millions of gates, and maybe 2 rare signal coming out, and there is a counter. This is synchronous counter, because clock is incrementing the counter, a specific value of counter, when that becomes, let us say I am just putting a random number 531, when this counter becomes 531, this rare 2 becomes, this is a rare for 0, this is a rare for 1, those 3 will make this AND gate true, and that becomes a counter clock for this counter. When this counter becomes 1, 2, 3, then this is the trigger condition. So, this is a synchronous counter, this is an asynchronous counter. So, there is a sequential, there is combinational. So, this is kind of a hybrid Trojan. An attacker can make it as complex as possible. So, your probability of activation is close to 0. Any question on this hybrid I am just showing only the trigger part. Similar innovation has been done on the payload side, I did not wanted to talk about, then that is going to take forever. So, there is this whole world of stuff, but from now on I am going to call them rare events, combinational, sequential, branches, non branches, electrical engineering, computer science, I do not want to talk about it, rare events. So, then all the subsequent discussion I do for detection we will be talking about how do we do detection of the rare events. We will talk about different things, but before I go there, can we stop this attacker embedding a Trojan? What do you think we can do? Knowing what you know now, what can you do to discourage the attacker for embedding a Trojan in your design? What will demotivate a attacker? Because attacker has to invest energy, money, whatever thing has to invest. What will demotivate them?
If you will not get some respective output, I mean in terms of money or
if they insert, they will probably get something out of it, but that is a good idea that end result is getting, let us say, ransom. If cryptocurrency is removed from the world, ransomware will go away, but you and I know that is not going to happen, at least not in my lifetime. So, then what else can we do? What is the threat model here? Rareness. If none of the signals are rare, all are equally unrare, then attacker has no place to hide. You try hiding anywhere, normal traditional validation technique will be able to activate it, will be able to detect you, right. So, then there are many methodologies, I will talk about something scientific perspective, but there are methodologies where you give the perception something as rare, but that is actually not non-rare. Something dark is actually in light, something in light has drive. So, in fact, this whole in security community, this whole honey trap business is you are actually inviting, attracting attacker to insert Trojan. In a place attacker thinks it is extremely rare, but from your perspective that is exactly where you are going to look. So, attacker is putting in a place that is exactly where you are going to look. But let me show you something from a scientific perspective. But before I do that, as I said, let us talk about metrics. So, in terms of metrics, what do we do from a, because we are going to talk about lot of detection techniques. If rareness is threat model, remember if threat model changes, all of these changes. Our threat model is attacker is going to hide in rare events. So, then if rare events is the rare nodes, then how the test cases you ran, this is functional Trojan detection. If you do non-functional, I will come to that in a moment. But before that, I wanted to show one more design that you probably did not see. So, this particular is always on Trojan. The other Trojan is you trigger when you want, it is always on Trojan, even then it is hard to detect. It is basically emanating the information. If you are doing any electromagnetic attack, then you can get that information out of it. It is always kind of writing to certain value, reading certain value, so that it is always on. There are many such variations, but that I will come to in a moment. But in terms of coverage metric, what I wanted to show you, if you are generating test or whatever you are doing, how many rare nodes you activated, how many rare nodes are in the design, that percentage, that is basically a good coverage metric. Then if you are thinking of rare branch coverage, same thing, number of activated branches over number of overall branches. Trigger coverage, now branch coverage and node coverage is not that difficult, trigger coverage is a serious problem. Anybody knows why? Number of nodes can be counted. Now think of number of signals, you exactly know, million. Number of branches, you know, thousands or millions of branches. Trigger is a problem because nobody told you, attacker never told you whether the attacker created a 2 input trigger, 3 input trigger, 4 input trigger. So, you have all these possibilities. So, that basically means if you have 1 million, forget about 1 million. If you have 100 signal, if you are choosing 100 choose 3 plus 100 choose 4 plus 100 choose 5 to whatever you do, this number is an exponential number. Even if you do not go beyond 6 or 8, this number is an exponential number. Even putting this total number of rare triggers here is an exponential number, and your probability of activating even a small fraction of them is very high. So, that is why the community what they do, they basically we understand there is exponential number of possible trigger, you randomly sample that space, randomly sample and choose 5, 10, 20, 100 and try to see how many of them you covered. It is kind of a twisted world, because attacker do not care what you are doing, they will insert wherever they can, but random sampling is the state of the art today. It may seem silly, attacker can hide anywhere, you randomly sample what is your odds or probability you will be able to activate, but that is the best we can do. This is an exponential number. And but the harder problem, even harder problem is the following. Harder problem is now we have all these number, I showed you only 3 metrics, how do I add it up? So, we were part of a $75 million DARPA project, they do not care, they do not want to hear any of those stuff. All they want to hear, I gave you a design, tell me how secure it is. That is all they want to know, they want to know something like this. They want to know from a Trojan perspective, actually they are not even interested in Trojan, they are interested in overall security. I talked about laser fault injection, I talked about FSM vulnerability, Trojan is one, information leakage I did not talk about. So, there are all reverse engineering, all these like the way Professor Karfa talked about, obfuscation and all that. Even if you put obfuscation there, how secure is it? And all these metrics they want one number. Why? Because when they are doing synthesis, area, power, optimization, they give one number, area is this, power is this for this configuration. They want one security number, so that they can then do different optimization techniques. If you say, well, for security I am going to give you 200 numbers, for Trojan itself I am going to give you 3 numbers, for information leakage I will give you 5 numbers, for reverse engineering I will give this much number, for side channel vulnerability I will give you that many numbers. What tool can do anything with it? So, the way we kind of tried doing is hand waving, you could figure out some weightage we are giving to node coverage, branch coverage, toggle coverage. If you do not do random sampling, actually these two values have no contribution. These two values have no contribution. Can anybody tell me why? Because this toggle coverage number, this number is so big, they basically dominate the world, right. But anyway, whatever it is, so we kind of came up with this and they are like unhappy about it, you could tell. And it is not just that, even if the number we get for Trojan, we have to do a weight multiplied this plus some number for information leakage, some number for reverse engineering, some number for side channel vulnerability or lack thereof. Even if you do mitigation on top of it, I will talk about some mitigations. Dr. Karfa talked about obfuscation. You want to know, did your security level improve or it did not, nothing happened or it deteriorated, you want to do that. So, that is why they are interested in getting one number, the way they get one power number, one performance number, they want to get one security number. And in the community people call it a pass optimization, PASS. This is area, this is, what is the other one? Oh, this is power, this is definitely power, that speed which is performance, that security, and this is area. So, area, power, performance and security, these 4 optimizations. When you go to industry, that is all you will be hearing, if your industry care about security, these 4. And let me just conclude with this discussion, that there are 2 ways company these days use this methodology, 2 ways. If you are an engineer joining a company, these are the 2 ways. If you are dealing with Trojans, you deal with another security level, story would be different. You have your design, you are doing rareness analysis, I only give you a glimpse how to compute, then you get your suspicious signals and branches, and these techniques I did not talk about, which I will talk in the next lecture. And through these techniques you kind of basically generate some tests, and somebody, not you, it is a blue hat red hat story, somebody in the company will insert Trojan in your design, take the design, do Trojan insertion, and then you are kind of running these different methods, either to compare the method or to figure out whether your design is good, then you kind of doing this analysis. Now, what does it give us? We are inserting, maybe our one group, we are evaluating, whom does it help? Can anybody tell me? It does not make any sense. I inserted a Trojan, you verified and say, yeah, I can detect the Trojan. How does this help? Think from, you are working in industry, think from that perspective, you are just wastage of money. Yes, please. Absolutely correct. You are doing all this to set up your environment, because your design is going to go all these places in the world. When it comes back, what confidence would you have that your framework would be able to detect the Trojan? Even the Trojan you inserted, if it is not able to capture those, then you know others you will not be able to do. But if you can capture all of them, you have good confidence we did build a good framework. You are just validating your framework. Recall the example I took. If you hired a bodyguard, you hire an attacker, make an attack on yourself to see how bodyguard defends, so that in a real world scenario you know how that bodyguard would protect you. So, this is the same analogy, and this is one way company uses. Another way company uses is, of course, still rareness, this part remains the same. When they have a golden model, and this is pretty much happens in design stage, not in when you have. So, you have a golden model, let us say C program or transaction level model, you may have RTL or get level model, you simulate and you compare the output. This has multiple assumptions, and one of them is absolutely wrong, which is you have a golden model. Most of the time industry do not have golden model, that is one. Second is it is a functional Trojan. I only talked about function. When I go into Trust Hub and benchmarks, you will see there are so many Trojans, and payload can be in so many ways. Functional Trojan is the easiest one to detect, because you can compare the output, you can figure out, assuming you can activate them. How do we activate? Then you will be saying, if the trigger condition is so rare, how is it able to activate? We will get to that. So, we stop here, and in the next lecture we will talk about Trojan detection. Thank you. There is no tea break?
Yeah, so we have 30 minutes break now. We already 5 minutes left, so please make it 25. Come back at 11:30. We have tea outside.
Good morning. In the last lecture, we talked about how to design hardware Trojan, and we briefly looked at how to talk about the coverage metrics of different Trojan detection techniques. And we looked at how do we look at rare node coverage, rare branch coverage, and the word rareness is pretty much everywhere. We also looked at two use case scenarios in industry, how it is used today for detecting functional Trojan, and as we go along other ways of detection, story would be different. Just to recap, you have a design and then you do some rareness analysis to identify where the attackers are likely to hide. If your threat model is wrong, everything else is wrong. And once you know where attacker is likely to hide through static or dynamic rareness analysis, then you have a set of techniques which I am going to talk today. You have a set of techniques that will provide you some test cases, and this test case based detection or simulation based security validation relies on the assumption that Trojan payload is functional. What non functional looks like, I will come in a moment, and if it makes any functional changes, then you would be able to detect them. And what is the key idea here? Somebody pretending as an attacker in your company, a good employee, would insert a lot of Trojan of different type. Ideally, you as a defender is not supposed to know your whatever method it is. We are proposing some method, you may manually write some more. Are you able to detect all of them, or what percentage of them you can detect? As I said, statistically, if somebody inserts a trigger more than 12 entries in an AND gate, the statistical likelihood is 0. You will not be able to detect, and anytime there is a 16, 20, you can forget about it, right. And as I said, there are usage models also where you have a golden model, then you can simply just see the compare the output and find it. So, how do you insert Trojan and how do you detect them? All these are interesting problem, and that is where the benchmarks come in. The key idea of the benchmark is when you develop a framework for verification, or you are comparing framework from two different companies, let us say Synopsys and Cadence, how do you know which tool is better? If you ask them to do it, then they will run on their design, which will make them look good. So, the idea of static benchmarks depends on whom you are asking. In this example, I am saying if somebody is giving you a Trojan detection tool at the RTL register transfer level or the high level, then the likelihood these are covered. What am I showing? So, there is a web page called trusthub.org. If you can go, you can look at now. So, it will give you sample Trojan in different categories. So, for example, where is the Trojan got inserted during specification design, during fabrication, testing, assembly, what abstract, there might be some overlap, what abstraction level that design is. Is it system level? Think of something written at system C or system C transaction level model, more like C, C++. Is it development environment? Is it register transfer level? Is it gate level design, layout, or at the beyond layout at the physical layer? Physical is basically like printed circuit board. Activation mechanism, how do they get activated? The trigger, always on, I showed you an example, always on, and then the triggered, there are more examples on the triggered category. Is it triggered internally or externally? Internally could be time based, condition based, something like that. We kind of created the AND gate trigger, that is a condition based. When certain rare condition is true, then it gets triggered. Externally, again this has to be triggered, but it is based on user input, or if you are looking from inside of a component, another component which is still a, you think of user input. So, if you are considering, let us say if you are considering, let us say a processor memory design, if this is a processor, this is memory, if you are thinking of from processor, you are sending something to activate a Trojan in the memory, if you are looking from the memory side, that would be considered as external. It is all relative perspective. In terms of effect, the payload, how is it? Payload could be you change the functionality, which is what we talked, because it is easier to discuss. Even for the detection, I will focus solely on the changing functionality. Do other Trojans exist? Yes. Do other detection techniques exist? Yes. It is easier for me to explain and hopefully easier for you to understand. Then you can, once you feel comfortable, you can move on to that territory. Degrade performance. So, that Trojan is supposed to slow you down, it will do certain things, your performance slow down. Let us say you are running at a gigahertz, it will make you, may not be megahertz, maybe 800 megahertz. So, degrade performance, leak information, that is actually a change functionality from a Trojan perspective is not that interesting, but leak information is a major objective. Information leakage is a key idea, whether it is a state actor like a country is trying to get information from another country, or it could be a company trying to leak information from another country, that is basically the leak information, right. When a company pays a significant amount of money to a third party to do some analysis, can you figure out all the system on chip in North America and their typical testing time, you know they are actually bribing you to spy on other companies, because they are getting similar requests from every companies, and it suddenly become legitimate for them. They are saying we are hiding information, giving you the average, but your intent is served. You want certain piece of information from other, then you can do membership inference attack and figure out what is Apple doing, what is Intel doing, what is Xilinx doing, AMD doing, you can figure it out. So, where what we call bribing in India, in US that called lobbying activities, that is legal. Bribing is probably legal here, that is why everybody does it. Once it become legal, maybe less people will do it, but whatever it is, that is basically leaking information, right. Denial of service is basically, you know, I mean you overwhelm a system so that it does not perform its task. Let us say an email server, you are sending an email, that server got bogged down, you are registering for or applying to IIT, applying for master's degree, PhD admission, that server is down. You just submit your application, then you do a denial of service, so that nobody else can apply. So, when Dr. Karfa is evaluating, there is only one application and there are 10 openings, you know the outcome, right. So, whatever it is, these are the effects, a lot of effects. Location, where is it inserted? I mean again this could be inserted anywhere in this website. These examples are available, inserted in processor, memory, IO, power supply, clock grid. In terms of physical characteristics, I only describe the easy one, functional one. It could be a distribution, it could be a size, it could be a type. Let me explain one more them so that you understand. The functional one changes the functional behavior, parametric one changes the parametric behavior. What does that mean? Power dissipation it changes, thermal behavior it changes. Now, on the surface it may seem to you like okay, what difference does it make? It does, because it comes with a cooling mechanism, how much it can cool. If you can suddenly increase the power portfolio and it become hot, every 10 degree centigrade change in temperature reduces the lifetime of the device by half, 10 degree centigrade, that is it, 10 degree centigrade. So, it can change the power behavior, and if we can talk offline how do we do that. There is a notion of power virus, temperature virus, but whatever it is, it basically do that effect, right. Same thing about layout, violating lot of layout conditions and all that stuff. So, this is I basically tried to give a very simplistic overview of what is out there in Trust Hub. There are many such websites maintained by European Union and other places. So, you can look at it, but if the whole space of hardware Trojan, whether you believe in hardware Trojan or not, some of the attack models applies to other domain itself. So, for example, two areas in security nobody complains, not in a single person. Trojan is like 50-50 split, information leakage and the side channel vulnerability analysis or attack. These two are going to stay there for eternity. How do you compute the leaky aspects of a design? How do you mitigate it, that line of work, and how do you estimate the side channel vulnerability aspect of it, which could be information leakage, and how do you mitigate it? Any questions on this? This is the threat model under which all of these operate. If this is an attacker came with something which does not even remotely fit this, you are not going to detect it because you did not design for it. Yes, please.
Is there a possibility of hiding
hiding one type of attack under a pretext of another one of those?
Is there a possibility of hiding one attack under the pretext? Remember, as an attacker you did not tell anybody. It is not those honest days that Devi Chaudharani used to say I am going to go and rob your house today at this time with these many people. There is no such thing. Nobody told you that, and as I go along you will see, even if somebody told you, even then you will not be able to detect. Even if they told you where and the trigger size of 10, go and look for a AND gate with trigger size of 10, you will not be able to do it. But yeah, it is possible. Is it possible to make complicated Trojan? Yes, there are. There are so many such Trojans, and if you look at publication, people are coming up with more and more difficult Trojan, and their experimental setup. We ran all the state of the detection techniques and all of them failed to detect it. If you are designing Trojan, that is your objective. If you are designing a detection technique, then you have to compare with other detection techniques, and none of them are capturing 100% of them, that is not theoretically possible. They are capturing 60% of the Trojan, you are like 77. As long as there is an intuition, and as I go along plethora of detection techniques, you will get an idea. Now, if you zoom in, so this is exactly it appears in Trust Hub benchmarks. I could pull in at the lunch time to show you. It has a lot more. So, basically you click any of them and then you would be able to download those benchmarks. You keep clicking what type of trigger, what it is, you just select and then you can download them. Now that we talked about the benchmarks, those are static benchmark. If anybody trying to sell you any tool, they already ran on all these benchmarks. So, static benchmark is good starting point, you can look how and what you can fill it, but from an evaluation of multiple tools it is not a good idea. So, what we came up with the notion of dynamic Trojan benchmarks, which basically means you do not have to give your industrial design to me to evaluate. You can take my Trojan detection technique or compare any two Trojan detection technique, but you have to use some Trojan insertion thing on your design, right. And you can pick and choose. We will show you the parameter space, which is like huge and potentially infinite. From that parameter space, this tool will automatically insert Trojans and they are valid Trojans. That is the catch. You can insert any crap in your design, but it may change the functionality, right, or it could be easily detectable. It will identify the rare places. It will if you tell them I need. So, if I go back a slide, you can tell them I need at the abstraction level of gate effect of degrade performance and this power supply with that many gates and all that stuff you can tell and spell and give parameter, and you can tell them how many Trojans you want. It is like a la carte, which food and all that stuff and which dessert, it will create those many Trojans and insert it in your thing. Now, you can ask two companies to give their tool and see how many of them gets detected. Of course, nobody will rely a Trojan detection tool to kind of insert in their multi-million whatever or $1 billion empire designs. Nobody will do that. It is like you are inviting a snake and feeding milk, but nonetheless this is a possibility for you, dynamic benchmark that you can do and mitigate. But as I said, the key idea is it is not only inserts the Trojan in the right places, right rare conditions, whatever you asked for, and then it also checks feasibility that is actually a valid Trojan. It will trigger, it will do everything, it will do that. So, as I said, the space is huge, what configuration you can ask for, trigger node and the current version of the tool that is available. What is the rareness threshold, how many Trojan, what is the activation mechanism, what is the Trojan effect, functional or leakage and so on and so forth. It does not support all space of possibilities, but it does support a vast majority of them. And here are some silliest example that you can look at your spare time, that if it is always on, then pseudo random generator and how do you and where we insert. Even in a silliest design, we can demonstrate you that we can enter different sequential, combinational, hybrid, always on, internally triggered, externally triggered, different types of Trojan we can embed. Now that we talked about metrics and benchmarks, which is basically the core concept in any security domain, I want to talk about something, how do you stop an attacker inserting thing with the notion of rareness reduction. There has not been a lot of work in this area, but I will throw some light so that you can kind of get an idea. So, what I am showing is a simple design is computing just this logic expression, and I wanted to show you if you compute statically the rareness, you would see that the rareness is 0.22, the least rareness in the whole design, ignore or number of signals with less than, if this is your rareness threshold, there is only one signal with that, and that happens to be this one with value 1, right. Now, if you just do optimization of this expression, as you can see this expression can be optimized, and the optimized version is this particular one. If you implement that, you will realize your lowest rareness is 0.25, higher rareness meaning it is less rare, and if you look at threshold 0.25, there are no signal below 0.25, if that was your threshold. Of course, ignore the all and average, but simply I wanted to show the act of, and it turned out we have proven that the most area optimized circuit has the least rareness. If you really want to make things rare, create a lousy circuit. So, then this kind of another opportunity for synthesis, when you are doing area, power, performance, all that optimization, you can squeeze your area, maybe performance is not good. You add more components like parallel ALUs, performance might go up. So, this puts you another dimension. If you want to do security aware from rareness perspective, then this optimization is good. So, one is this discourages attacker from attacking. This is one way I am saying, it is basically I am saying you, right. The rareness is, there are not too many rare signal. So, you do not have too many places to hide, right, that is what I am saying. But how do I prove it? To prove that, we run on different techniques. Of course, I did not talk about the techniques yet, but different techniques like statistical testing, which I will talk in a moment, and satisfiability based detection and all that, and you would observe that if you have same design with the lower area, then your detection, so this is the reduced area, then their detection probability or detection accuracy goes up. So, just if you take a specific point, trigger size of, let us just take a trigger size of, what line am I drawing, maybe trigger size of 6, then if with your original area, if the detection accuracy is 60%, with reduced area your detection accuracy is almost 80%. So, using your existing detection tools, your detection accuracy goes up. That is another way of saying it is not motivating for the attacker to insert if rareness is low. So, this is one of the approaches, reducing area. There are many approaches, we looked at many other things, I just want to talk about 2 of them. This is another one, is design diversity. If you are creating adder, all adders are not equally friendly or unfriendly to rareness. So, in this example, so one aspect is still area, the area story still holds for same design. So, if you are looking at carry look ahead adder, the high area story would still have kind of better detection accuracy, and so this side is basically average rareness of most rare 100 signals, but whatever that number is. So, the rareness story is kind of aligns with. So, this shows 2 story, one is area has that effect earlier, second thing is same adder, same addition operation, depending on how you implement it, it has a different portfolio in terms of rareness. For example, this particular design I do not remember what it is, it is so in terms of its rareness is 0.6, which is hardly rare, it is hardly rare for particular value, whereas some others are 0.2, for example, this design and this design, I can see what it is. This is carry save adder, carry look ahead adder, half adder. So, different design. So, we do that for our sorting algorithm, right, depending on performance you choose different sorting algorithm, depending on your rareness, assuming there is no problem with their kind of So, of course, area also they have a problem. You see this particular design, the area requirement is very high, although their the portfolio sorry, this one was wrong. So, this dotted line. So, the portfolio wise the area is really low, but I am saying it wrong. Rareness is really low, extremely rare, and area is in this case really high for that particular design. Any questions? So, design diversity, area optimization, there are many other optimization opportunities you can do, and you can control rareness, make it unattractive for the attacker to insert trojans. There is another way to demotivate attacker. Any of you know that? Dr. Karfa will cover whole day on it, obfuscation. Because what was the primary objective? Designer has a clear idea of your design, they can simulate it, run it, analyze it, find rare values. If you obfuscate it, confuse the reader, the attacker, and you put let us say few more extra transitions, and you just make random moves, then attacker has no clue what it is computing. Attacker will not be able to figure out what is rare, what is non-rare. So, then obfuscation is another methodology, rareness reduction is one, and some of you guys will come up with other ways to discourage attacker. So, this is you can think of this is design for security solution. So, you are designing something so that it is attack unfriendly. Now, I am going to talk about different Trojan detection method, and as I go along I will introduce many ideas. Each of the idea has publication on AI. I will not get a chance to talk about all of them, but I will talk about during statistical testing I will talk about Shapley value analysis, that is an explainable AI technique, and reinforcement learning, during side channel also few of them, and golden free detection, of course, all of them are based on AI. So, I will sprinkle those, but I will spend some time on throwing the key idea, because machine learning is trying to figure that out anyway. Because first I want to show you how manually you can do it, so that whether you use machine learning or whether you use non machine learning, the technique remains the same. So, here is the big picture what is going to come next. When you want to do Trojan detection, you can do normal simulation based solution, you generate test, run and detect, or you can do side channel based solution, exactly what Dr. Karfa covered earlier, side channel based solution. And even in side channel, depending on what side channel footprint you are going to use, is it current, is it delay, is it electromagnetic emanation, solutions are going to be different, drastically different, I will talk about. Similarly, here itself I am going to show you at least 6 or 7 possible solutions, just test generation. It may seem to you like, well, I just generate test and run and detect the Trojan, try activating the thing, but as you will see, yes and no, and you will see how it goes. Any question on this big picture? We are doing test generation for simulation based Trojan detection, or we are doing side channel analysis based Trojan detection? Yes, please.
One question is, these two methods, can they find the same kind of Trojans, or they are targeting different kinds of Trojans?
Absolutely. So, the question is who is good, who is bad, it is all relative. As I go along, I am going to present the works in the sequence they are published. So, then it may seem to you this is better than them, but as you see next person comes in, and it is not like functional ones were published first then side channel one, it is kind of mingled, although I will present them separately. So, there is no right answer, it is really every solution is trying to improve on the previous solution. So, all of them are equally good or equally bad.
So, what is the key notion of the side channel? What is the side channel of Trojan?
So, side channel of the Trojan is basically, so for example, when you are doing the path delay based, the Trojan insertion circuit and Trojan not inserted or Trojan free circuit has different delay characteristics. We are trying to figure that out, because if you put an AND gate in the path, then that AND gate is supposed to introduce a delay, but that delay is supposed to hide in process variation. How can I expose it? Same thing for the current, if you have 3 gate, 5 gate, they are going to consume or produce extra power dissipation, that is very tiny in the bigger story. How do I amplify that? How do I hide everybody else, ask everybody to come down, and only the Trojan gets to shout in full voice. How do I do that? So, that is why I put that down, maximize activity in suspicious region, minimize activity in the rest of the design. That is the key idea. So, that we can, whatever technique we are using, electromagnetic emanation, delay or current, we can amplify that. Any other questions? So, now so again assumptions for Trojan activation is basically that AI, the Trojan is activated lower probability and triggers are selected from rare nodes. With that assumption we will proceed. If things change, a story will not change. So, here is a trigger that used ABC, and but you do not know whether it used ABC or not. So, if you are trying to detect Trojan, you have to assume A, B, C, D, which are rare nodes based on rare analysis. You have to assume, you have to try to construct trigger for all possible scenarios, and this for 4 nodes 2 to the power 4 minus 1, all 0 is not a scenario, you are not taking any of them. So, 2 to the power 4 minus 1, those many scenarios you have to consider, and for each of them you have to create a test case. How do we create? We will come to that later, but I want to just convey you, if there are n rare nodes, 2 to the power n minus 1 possible trigger condition. And where does this n come from? You simulate, you see how many times it is 0 and 1, you put a rareness threshold, and anybody below that threshold you call them rare. So, in a million gate design, if you have rareness threshold of 0.1, about thousands of signals would be rare, 2 to the power 1000, you get the feeling. There is no way you will be able to consider all these scenarios and generate test for them. You artificially you can reduce to 0.00001, but you do not know what attacker is trying to do or how many, which signal they are trying to take. But the point I wanted to mention to you, even if you know it is rareness based trigger, the number of possible triggers is exponential, huge. So, you will not be able to try and generate one test for each of them. Yes, please.
To the power n minus 1 possible triggers are there. So, in reality we will take only one of them or all of them?
If you are a defender, you are trying to generate the test, you do not know which one attacker did. So, you have to consider all these scenarios and generate one test for each of them.
So, like the previous example that we have taken for the AND gate, there are 5 inputs. So, only one of them.
Let us not consider previous gate. In this example, this trigger has 3 rare input, but you do not know attacker actually created this, you do not know that. All you know, your design has 4 rare signal A, B, C, D.
Oh.
So, you have to consider all scenarios, because attacker did not tell you I created a trigger of size 2 or trigger of size 3 or trigger, attacker will never tell you, you do not know that. And remember, this is what we are doing design time. The Trojan might not get inserted in design time, Trojan may get inserted during fabrication time. So, you want to generate test now, so that after fabrication when it comes in, you can run the test and you can take exactly the way manufacturing defect story. You want to create manufacturing tests even before it goes for manufacturing. When it comes in, you keep running those tests and say, oh well, that wire was drawn correctly, that transistor is formed correctly, tick, 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 tick. You do for all of the millions of lines, same analogy. Go ahead, please.
Sir, for input size n, why 2 to the power n minus 1, why not 2 to the power n?
So, because minus 1 is the one possibility, all 0, that is not even a trigger. All 0 basically means take none of them, then that is not even a trigger. So, and it should not be a surprise, this I showed earlier and I said I will come back to it. So, even a tiny design with 451 gates, think of 451 variables, there are 10 to the power 11 4 even if attacker told you it is a 4 input Trojan, 10 to the power 11 is a huge number. It is solvable, but it is simply if somebody did not tell you, so it is going to be even more, and if we cannot solve something for 400 gate design, think of million gate design, what are you going to do? It is not possible to. So, those many basically input scenarios you have to try. Now, I am going to talk about lot of techniques, and those techniques basically generate tests, assumes it is a functional Trojan, that is the reliable story. So, let us start with the first one. So, this is in 2009, remember 2007 DARPA started funding, this is one of the first or second paper by Professor Chakraborty from IIT Kharagpur. And so, the idea of MERO is multiple rare occurrence, and this came from an idea of Professor Edith Pomeranz's work on N-detect in manufacturing testing community. The idea is very simple, and very elegant. The idea is, if I know what are the rare signal, if this is my design, and let us say I have 3 rare signal, and let us say I have many other millions of non-rare signal, let me try to make them blue or some color. I have many more non-rare but regular signal. Idea is, let us try to activate each of them n times. So, what am I changing from? Earlier my problem was the number of inputs, this is exponential. So, I cannot try all possible inputs. So, this is not possible. Then I will be trying random inputs, and in the random input I will be keeping them in my front pocket, the ones that activating some of the red ones. If they are activating, if any test activating 2 of them, that is even better. If any of them is activating 3 of them, that is even better. But I only want to keep the ones or maintain the ones that are trying to activate each of the signal. It would be nice if I can maintain a queue of somebody who activates 2 at a time, 3 at a time, 4 at a time, because that is how triggers are. But the counting game in this work is only one of them. I keep a test if it activates one. So, think of every node, how many times this is getting activated. Every time you run a test, there is a counter for each of them. You kind of figure out how many times this got activated. Let us say last I ran 10 tests, this got activated 5 times. Now, I ran another test, this got activated. So, I make it 5 plus 1, 6 times it got activated. Every rare signal has a counter. You run a random test, you decide to keep it or ignore it. If you decide to keep it, then increase the counter accordingly, which one it increased. Now, here is my question. Do any of you have a question? Because if you do not ask question, I am going to ask. You run a random test, and you after simulation you observe who got activated. Now, what does activation mean? I need to explain that too. I did not explain. Let us say here is an AND gate, one of these signal is output of an AND gate. This is not the trigger, forget about the trigger for a moment. So, activated basically means earlier it was 0, it got changed to 1, or earlier it was 1, it got changed to 0. That is what activated means. It changed the value, it created a switching or something happened, right. So, that is we call as an activity, right. You apply a test that created an activity there, you increment the counter. Now, that none of you ask question, my question is, we know trigger will not be based on one signal, most likely attacker is trying to make it more rare. So, they will put multiple of them. Why Dr. Chakraborty used one counter, why not 2 at a time, 3 at a time or 4 at a time, a counter of those, because likelihood the trigger would be 2, 3 or 4, that counting would have been better, is not it? Why not? Because the number of counters would be exponential, that would be more accurate, more precise, but if you do 2 at a time, even if your rare node set is 100 nodes or 200 nodes, the number of counter would be exponential. Now, this comes from a statistical theory borrowed by Professor Edith Pomeranz, then they borrowed. Idea is, if you can activate each node n times and in n is sufficiently large, let us say 1000, then the probability of activating the Trojan, does not matter whether it is created using 2 or 3 or 4, goes very high. Take a moment, think about it. We are only observing one person in the society many times, doing some auditing or whatever. Even if multiple people in the society is trying to do something, a terrorist attack, we will be able to find it. But we are not considering multiple people at a time, we wish we could. One person getting activated n times. Can anybody give me an intuition why that this works? Statistical proof you can see later. Sorry, no, not herd immunity. Because when you are activating this n times, it is going to activate other folks too together. So, if the attacker is actually creating a Trojan out of these two, if this is getting activated n times, this is also getting activated n times, may not be at the same time, but the probability of these two getting together activated at the same time goes high. Another way think about it, if think of these rare signals is only on this side of the wall, all other walls are non-rare. Even if I blindfolded and I am throwing a ball to the wall, if I randomly throw the ball to every possible wall, my probability of success is low. Even if I am blindfolded, I could turn this way and keep throwing all my balls to this wall, my chances of hitting those rare signal increases. Probability compared to what? Compared to randomly throwing on the every possible wall. So, that is basically the key idea, right. So, n detect relies on the principle that you are trying to activate only the rare one, you do not care about the other folks, because that is not trigger created with, that is one. Second is when I am activating this n times, there is a high likelihood these two or maybe these three together would be activated at the same time. Yes, please. If the thing becomes on, can you check? Okay, go ahead please.
So if it detects, so one trigger can trigger other ones.
May.
Okay.
Statistical likelihood.
Okay.
That's why this is called statistical testing.
Let's say it is. So is it counted?
No, it's not counted, because if you keep counting 2 at a time, 3 at a time, then even if you have 100 or 1000 rare signal, 1000 choose 2, 1000 choose 3, those combinations, if you add it up, that's exponential counter. In real memory, we won't be able to maintain that many counters.
So let's say if I trigger one and it starts triggering others, for a few seconds or for a delay, it creates a chain reaction, right? And then it dies down.
Implement the program
Okay.
with multiple counter in that lunch break, then ask me.
Okay.
Here we are maintaining one counter for each rare signal, and counting becomes easy. When you want to do pair or who else it's contributed, the number of counters would be exponential. Any other questions? Okay. So, now that we have that covered, this is the basic one, and the key idea is so you start with a random number and then you want to flip a bit. In this example, we flipped the leftmost bit and we observe before flipping and after flipping, is there any change? If before flipping it was flipping one of the red, after flipping also is still flipping the red, we do not want to take that one. That is the mirror philosophy. Same, and we flip here, initially it was doing 1, before flipping, after flipping it is doing 2. So, then maybe we want to keep it. So, exact number, how many, that is different, but I am just telling you it is basically a bit flipping algorithm. It is not just what I said initially, you run some random test and keep the random test that you find thing. It is basically you run a random test, and if you like it, then keep that version and flip one of the bit. If you do not like it, do not flip that bit, try flipping another bit. Now, does this remind you any of the AI algorithm? Of course, AI was not that popular, later other people published including my group. What algorithm does it remind you? Keep the one you liked, do not keep the one. So, all of these ideas when you read, you will say, oh, this could be applied for AI. We will come back to that in a moment. Problem with statistical approach. Statistical approach or this Mero approach has two fundamental problems. Can anybody tell me what it is? It relies on the principle of n detect, but it is just that in a design of 100 rare nodes, some of them would be extremely rare, some of them would not so much rare. So, that is why you will see some of them are really barely covered. So, maybe like 1 times, 2 times, some of them are not, you wanted to cover everybody, hit everybody 1000 times, but some of them are covered 1 or 2 times, some of them are covered millions of times. And if you try to make the rarest of the 1000 times, then you have to try trillions of tests, it is not going to work. So, theoretically it is wonderful, practically it does not work, because it boils down to bit flipping, which is exponential by itself. You flip every possible bit. And so, for different design of course, but what I just said, then this results in the paper is not possible theoretically, but this result is also correct. Can anybody tell me why? What I just said, you take any design, there are rare nodes, you keep counting, even if you go for millions, some of the rare nodes would be millions of time activated, some of your objective is 1000 times to activate each of them, at least 1000, but the rarest one probably activated once or twice, that is the reality. But when you look at the design, these are the ISCA's benchmark, it is reasonably good 80, 70, 80, 90, 100, 90% Trojan detection rate. How come? There is something silly about these toy benchmarks, and I will come to that in a manner, but I just wanted to put that idea in your head that even if something seems impossible, the numbers when you look at, do not assume that is flawed results, it works for those designs and there is a reason. Now, I want to talk about something else. Remember, we are doing the counting. So, when we are working on this problem and we thought, wait a minute, if there are 100 rare nodes, why do we generate millions of test cases trying to activate each n times and hope and pray that my trigger would get activated. If I go back and draw the same diagram, so this was the idea for the next work. If I draw the same diagram, let us say I have 3 rare nodes, why do not I try to come up with one test case that would activate all 3 of them? If I have 100 rare nodes, I will create one test case that would activate all 100 of them. Then does not matter what attacker does, which 3, which 5 the attacker took, my test is guaranteed to cover it. Think for a moment, if I have 3, what I am trying to do, come up with one test, no million, no exponential, no counting, to cover all 3 at the same time. Can I do it? That is a different story. I will come to that in a moment. How do I do it? So, the two extreme, I think I have an animation also. One is the Mero work you look at, where you cover one at a time and hope and pray that actual trigger got activated. Here we are saying you do all at a time and praying is not needed. You cover all at the same time using one test case. Now, if 3 is the total rare nodes in the design, whether the attacker uses one of them, 2 of them, all 3 of them, it does not matter, the test case is guaranteed to cover.
But you may not have test case of such category.
Professors are not allowed to talk. I was about to ask that question, because if you try to cover all of them, because the way design is, such a test case may not exist. There may not be an input pattern which would activate activating such a thing is hard, there may not be an input pattern. Then what do I do? Even before I go there, what do I do? I wanted to cover all of them, I could not cover all of them. So, let us say here are the 4 nodes, ideally I wanted to cover all 4 of them. If I could not cover all 4 of them, I could not find a test that would cover all 4 of them. What is the best I can do next? Anybody else? Most it can cover. So, that is in computer science that is called, let us say I will try 3. So, this 3, that 3, I am sure there are many other possible 3s. The next most is 3 at a time. If that is also I cannot cover or some of them, then 2 at a time. In computer science, what does the algorithm sounds like? What is it called? Huh?
Greedy.
No, not greedy. It is maximal click sampling. These are the clicks, largest possible one. So, basically you are trying to find the largest one, try to activate it, whatever largest you can do. So, maybe you can do these 3 and then this one is left, maybe then you will try 3 or try 2, you are trying to cover those. So, this is the other extreme. So, you still have that story of trigger sampling and all that stuff, but the key idea is, so you are doing repeated maximal click sampling, you are getting those clicks and getting a test case for those, and then you do evaluation. And I am not going to get into the detail, you get the satisfiability graph. If you do not know, do not care, it is not. So, you start with the design, get different clicks that are satisfiable, and generate test for those clicks. So, it is still two different extreme, and basically then there are proof, you can look at the thing, valid trigger, and so basically you are mapping your Trojan detection problem to click cover problem, and once you map it to the click cover problem, then you find a test to activate that click. I believe I have animation, but let me see how it goes. So, the 4 nodes I was talking about with different functionalities, then you are really what you are doing, you are let us say when you are trying to do this intersection, what you are asking the satisfiability solver, if you remember SAT solver, we gave a bunch of expression, it tries to come up with assignments to variable such that the expression is true. What you are trying to do, this expression and this expression is true. Let me see whether you guys are with me. Where did I get this expression? From here, how did I get this expression? This expression is nothing but looking from the input all the way, computing this function, start from there, go back and compute this function. So, D is equal to, let us say this is T1, this is T2, right, equal to T1 or I do not know how to write or T2, right. Then T1 you are finding this XOR. So, you basically keep pushing those stuff, that is your expression, right. So, theoretically this is a wonderful idea. What do you think is a practical problem? Remember, I ordered the papers in that order, the order they appear. So, it may seem like, oh, this is great, but then I will say what is the problem, then the next one. What is the problem with this approach? In this diagram it looks nice. When you have a real hundreds and thousands of gates, this expression is going to be huge, and giving to any reasonable SAT solver, handling all these conjunctive normal form, their intersection, that SAT solver will fail, even if it is satisfiable. Even finding the time to tell you it is satisfiable, that is going to be a problem. Then there is another problem, maximal, I quickly flip the slide, maximal finding this story is, you see, 3 to the power n, it is not even 2, the number of clicks and all of that, that is also exponential. So, when we started solving this problem, we did not realize the bit flipping exponential problem in the statistical testing, we moved that problem to the click finding problem, click finding becomes satisfiable, that become exponential. So, when you are solving problem facing such a story, in fact, the bigger problem happened here, constructing the satisfiability graph, that itself is exponential. So, we basically borrowed another idea from computer science called lazy construction. So, do not construct the graph until it is absolutely needed. So, all of this stuff we had to do. When you do any research, you will be simply developing the theory and proof stuff, but practically they may not meaningful unless you do lot of engineering effort to actually make it run on large designs. So, there are a lot of animations, but I am going to skip all of them. Basically, when you start with something, your objective is to construct with all 4, and you start doing, you see DAB, it is not based on this expression, you give it to SAT solver, it will not find a solution, that went red. So, then you walk back and say, oh, forget about B, now let us try DAC, that is also not satisfiable. Then you say, okay, how about DA, okay, that is satisfiable, DA or AD. So, then basically all you covered at this point is this click you covered, but you are trying different ones. So, this is this you covered, you are seeing which of them together satisfiable. SAT solver can find assignments to those variables, so that they are true at the same time. If they are true at the same time, the primary input that makes them true at the same time is basically the input that activates that click, and that is the test case. And if the attacker actually chose this as a trigger, this as a trigger, or these two as a trigger, this test case will work for all those 3 scenarios. So, similarly, I tried constructing for this silly example other ways, and here it is a 3 ABC. So, ABC is earlier we showed AD is satisfiable, now I am showing ABC is satisfiable. So, there is a test. Similarly, we just you can construct and try to give the SAT solver the story, and BD is satisfiable, and so on and so forth. And when you show results, you kind of have to still compare. At that point the mirror was the state of the art, you have to compare, and so in terms of your test length, coverage, how much you cover, how much is test generation time, how you are doing compared to state of the art. And so here is another visual of number of test vectors you keep increasing, and then you see the trigger coverage for random, because these are rare, this is what random is expected to do. We got only 3000, even if you go from million, it may not move much, because those are rare signal by definition. So then you do Mero, it is going to go up certain number, and then you do 80%. Again observe, in the Mero paper this number is not 40, this is 80, 90 or 70, 80, 90. So we will show you why that is still consistent. Now we will go to machine learning. Just to give you an idea, anything I talk about here, you can apply AI on top of it. So we just what we did statistical testing on Mero, how you can apply AI on top of Mero. Remember what was Mero trying to do? Take a pattern, if you like it, you flip a bit. If you like that bit flip, you keep it, otherwise you change it, right. So typically you could do such a thing with genetic algorithm, or you can do using machine learning. I am going to show you reinforcement learning. If you want to do genetic algorithm, anybody studied genetic algorithm? They are all cousin brothers and sisters, machine learning, genetic algorithm. Anybody knows how it works? Yes.
It works with mutations, so we introduce new changes.
We introduce new changes, right. So in Roman days, there was an emperor who basically did not allow any soldier who did not win, if they died in the battlefield, problem solved, that person is not allowed to produce child. Because the idea is, if you won in a battle, if you are healthy, then the child you produce, that is going to be healthy, you will go to war. So whether that biologically that is true or not, we do not know, but in genetic algorithm, any bit you flip, if that bit brings a lot of thing, that is a good choice you want to keep, retain, and subsequently let us say you have 4 bits, and think of a tree, you have 4 choices here. This bit flipped from 0 to 1, this bit flipped, and so on and so forth, and each of these choices either you keep and that subtree continues for the other bits, or you do not keep it. So certain choices you keep or allow it to mutate, certain choices you do not keep. In reinforcement learning, before I go there, I want to just summarize what we talked, 2 techniques we talked about. One is simply by statistically create. So this is the notion is n detect, make each of them activate n times, and this one is click sampling. You basically get the clicks and try to get a text. Try to do all of them at the same time, one at a time. That is the idea, too extreme. And so what is reinforcement learning trying to do? Did we introduce reinforcement learning in this class? We did, right? Which of you can explain me what reinforcement learning do? You learn, it reinforces. Yes, please.
So in reinforcement learning, firstly we have to define what is the objective. Based on the objectives, then we set the defined rules which will either reward the agent or it will penalize them.
Reward and penalize. Ivan Pavlov's experiment of ringing a bell and dog eating, even the days reinforcement learning was not known, that is basically the idea. You get, so there is an agent, and so agent interacts with the environment, it is a certain action, and the possible action with the environment depending on the story, environment interacts with the state, and then basically if things are going well, then you reward. Think of in this particular story, if a bit flip actually activate certain thing and you want to keep that test, then that bit flip you want to reward or increase the weight. Simply speaking, do not, for the subsequent story, keep that bit in that state. But if certain bit flip did not help, you just go back, do not flip it, do not, for subsequent iterations, if out of these 4 bits you tried changing from 0 to 1 and it did not like it, go back to 0, and for all other experiments this bit is fixed to 0. That is the basically penalty or punishment. There are many other ways. So that is basically key idea of reinforcement learning. And what is happening here is, so there is a little more to this. When you do, 2 other ideas I have to introduce. When you want to do this reward, how do you compute reward? Remember in In Mero they are computing by counting how many it activates. So, this is not the counting game, this is based on scope or Sandia controllability, observability and lead program. Again you can download it and play with it. Anybody knows what is controllability and what is observability? So, in controllability basically means if this is your design and there is a rare signal in this context, rare signal means can I come up with input assignments or how easy for me to come up with input assignment to change or flip that value, that is the controllability, right. So, you are trying to assign that controllability. Observability is I thought I controlled it, how do I know until I propagate it to the primary output. So, this part is controllability, control and this part is observe, and this is the key idea of what I am going to talk next on automatic test pattern generation. You control and you observe, right. If I fricked you enough you might be start crying, but you might close the door and cry, I may not be able to observe. It is controllable, but I could not observe what happened. I threatened you and are you collecting money from the bank to give it to me. So, I do not know. So, until you give the money I do not know here, and this is a key idea which I am going to bring in later for automatic test pattern generation. But for the remaining part of the lecture let me briefly talk about controllability and observability using a simple example. Let us say you have an AND gate, right, and let us bring the context of manufacturing testing. Manufacturing testing, let us assume the threat model, they called it fault model. The fault model is that this particular line is stuck at 0, stuck at 0. So, how is that possible? When the fabrication lab is drawing a line, it might got connected to the ground line. No matter what you do, it is just stuck. Stuck at 0 is one fault, stuck at 1 also another fault. So, to test stuck at 0, and so initial threat model is all the lines are stuck at 0, all the lines are stuck at 1. So, for each of them you have to generate one test. So, if you have a million line, you have 2 million tests, one for stuck at 0, one for stuck at 1, but in reality it is much less than that, because a single test can cover multiple of them. Let me show it to you. If this is stuck at 0, how do I test it whether it is stuck at 0 or not? Remember, I do not have visual access, the boundary is somewhere out there far away, it is fabricated, I cannot see it inside. I know how many gates are there, I know which gate I am referring, what its name, A, B, C, D, E, F, G, I just do not have manual access to see it or probe it. How do I do it? Whether this is stuck at 0? I have to disprove it, right. If it is stuck at 0, I have to try to make a 1 here. To make it 1, what do I have to do? So, I have to somehow make this 1. So, controllability of 1 here again. So, I have to, this is the cone of logic I am considering. To make it 1, I have to make it 1. So, that means controllability, let us give it a name A, B and C. Controllability of C can be achieved by controllability of A and B, and stuck at 0 test for C, same test will work for stuck at 0 of A and stuck at 0 of B. That is called test compaction. So, this is a full semester course, but I am not going to go through that, but this basic idea I will use later. So, this is the controllability story, you continue this all the way. It is just that life is not that easy, many times you keep going back, there will be conflict. When there is a common logic, this path is saying make it 0, this path will be saying make it 1. Then it is a serious problem, backtracking. This is the controllability problem. Anybody has any confusion about controllability problem? We are trying to make a line a specific value. Why? In manufacturing testing, because it is a stuck at 0 we are trying to do. Now, the observability problem, how do I propagate? We believe we made it 1, we believe, but we do not know that for fact until we propagate to the primary output or to register that we can dump. To illustrate, let us assume there is a output OR gate, okay, and let us say that is the primary output. For this value to propagate, what do I have to make this OR input to? What do I have to make? What value do I have to put it there? There are two, this is a Boolean value, either 0 or 1. How many of you believe this should be placed 1 in a OR gate? How many of you believe this should be a 0? There are 2 hands, this should be 0, because in a OR gate if this is 0, 0 will propagate, if this is 1, 1 will propagate. If you make it 1, it does not matter what this value is, always output would be 1. So, we have to make it 0. So, to make it 0, it again becomes a controllability problem. So, observability problem for variable c can be achieved by controllability value, let us call it ABCD, the controllability of signal D with value 0. So, this is basically observability, controllability, it just goes, it is a very interesting problem, and this algorithm is used for eternity, right. So, the scope actually does all of this for you, and you do not have to worry about it. There are many other tools, I prefer this, but in the next lecture we will basically use this controllability observability story to kind of solve the other remaining problems. Thank you.
So we are done with the first half of today's lecture. Thank you again all joining Sunday. It's not easy to come on Sunday to class, right? Today, just to make you more time, what we will do that we will make the lunch hour 1 hour. Right? We have very simple lunch outside. Don't blame me when the lunch is not too costly because I have budget constraint. And we will come back after 1 hour and we will try to finish by 3:30 at most. Even some problems. Okay. Thank you.
discard. No, go up, right there. Good afternoon. In the last lecture, we talked about different ways of detecting Trojan using statistical testing, and what we are trying to do now is how do we extend some of those ideas to use AI algorithms. So, specifically in this one we are talking about reinforcement learning, and the key idea we are trying to extend with reinforcement learning is when you have a set of bits or a pattern and you are trying to do the bit flip, how do you do those bit flip efficiently. And in this context we introduce the idea of reinforcement learning, where an agent monitors the activity, and if the activity is towards positive direction or favorable to the objective, then you reward it. If it is not favorable, then you penalize it. In the specific example of our case, we are doing bit flipping. You either keep a bit flip or you permanently mark it as should not be flipped. And to do all of that, basically we need to use the metric somebody favorable, not favorable. Then the metric is basically scope. So, basically the values or the signals or a specific bit flip, did it make somebody more controllable or less controllable, more observable or less observable. All that metric we basically computed using one of the open source library called scope, and it has a lot of internal details, different values it gives, and you make use of that to compute whether to reward or keep the flip or whether to penalize or undo the flip. And again all these values you can compute with respect to the primary input and primary output. Some of the sample calculation for a specific gate would look like what you are computing for minimum of A and B, and for OR it would be some similar story, for AND it would be similar story. But basically you already know testability of a specific variable with respect to the testability of its input. You can compute that recursively, and once you have that, then the story exactly same as normal reinforcement learning, which is you have a design, then based on the information that you need, in our case it could have been just rare node and which would be just fine. Rare nodes as well as controllability and observability metric, then you basically you have a probability distribution of whether to flip somebody or not flip somebody, and you go back. So, I wanted to highlight two things. One is, if you recall our statistical original solution of Mero, we are essentially still trying to find a pattern, still trying to find a flip, and in that case we are saying which flip will help in the end detect. That was the criteria. Here we do not have that criteria, we are going for controllability and observability, but you can still stick with end detect criteria. It is just the flipping mechanism you reward in terms of the controllability idea. So, no matter what idea you have, if you can clearly define the objective, reward and penalty, you can use reinforcement learning. Any questions? And in this particular case we are feeding this kind of testability metrics. So, in terms of broad overview, so basically once you have the probability distribution, we are computing probability of flipping the bits, and then you basically provide it to the design, you still count the number of switches, and then essentially you continue that process, which is exactly same as the original algorithm. And in terms of number, of course, you would expect it to improve, and I am going to skip that. Similarly, for test generation time, so yes.
How better is this compared to random test generation?
So, Mero is better than random. So, question is how better is compared to random. Mero is better than random, because random is trying to throw balls at every possible wall, and Mero is trying to throw the ball exactly to the wall where the rare nodes are. And these were supposed to be better than Mero, because Mero is flipping the bits based on a heuristic, and this is more AI enabled, so it has better insights. That is why it is going to get better than Mero as well as better than Tarmac, activating all of them at the same time or activating some of them. Random is always the, so in terms of test generation time, the key idea you can look at both ways. So, typically in this community, if you want to publish, you have to get to two assumptions. One is either you generate same number of tests and compare who is doing better, or you go for a specific, or you can keep running and see who is saturating at what coverage level. You can do that. You fix the time or fix the test, or you fix a coverage and say to get that coverage who is reaching faster. So, that is the test generation time. Otherwise, you can infinitely keep on going and generating. So, once you fix somebody, then you get the another aspect that is important specifically for kind of AI algorithms, any AI algorithm, is the stability. So, in terms of when you run on different benchmarks, then you want to know when you do different trial, try different times, start even if you are doing random test generation, you start with a different seed, is it stable, is the result stable or oscillating. So, then that is not a good algorithm, even if it relies on random, which is not a problem, but no matter what seed you start with, it gives you same result, could be bad, could be good, but when it oscillates or move around the trigger coverage or any metric, that is not a good idea. In this particular example, at least in this particular scenario, reinforcement learning, first it provide better coverage, that is one issue. Second is the coverage is stable across different trials. So, any AI algorithm, there are many things people look at. This is one of the thing, the robustness, how kind of stability of your algorithms with respect to different variations. Now, I am going to move to another domain, again it is ATPG, the idea I already talked about, controllability and observability. I am going to make use of it. So, ATPG stands for automatic test pattern generation, and the idea actually originated in manufacturing testing domain. And I briefly talked about manufacturing testing, but just to recap, when you do the fabrication, when the chip comes from fab, remember there are millions of them coming. So, for the processor it could be thousands to millions, for the memories it could be millions to billions of copies coming in, and there is something called automatic test equipment. You put each of the chip, remember millions of them are there, you put each of the chip on the board, run those tests, and then either it passes or it says, oh, there are few lines which are defective, right. Then at that point the company decides whether to throw in the trash bin or try to make use of it. So, for example, if few cache lines are bad, so then if it was, let us say it is a 128 megabyte cache, you have an option of selling it for 64 megabyte by disabling the remaining part. So, then there are economical choices, but no matter what it is, the key point is the amount of tests that sitting here, the tests I generated based on controllability and observability, those are the tests sitting in that tester board. You put a chip, run all these tests, and then throw the chip either left bucket, right bucket, or middle bucket where you want to sell it for a lower profit margin. So, number of tests is actually important. if you can reduce it, because it is a multiplicative factor of you are going to run it for millions of chips. This is slightly orthogonal idea to functional verification, where you do once, twice, 5 times. Here you are going to do millions of times, and the memory of these devices, are the cost of this automatic test equipment is decided by the amount of memory you have. And without getting into the details, you have to understand, you are designing a 4 gigahertz processor and the board has to run on a 4 gigahertz, although board is using a processor of the past generation, which could be 2 gigahertz. So, running a 4 gigahertz processor at speed using a 2 gigahertz processor, that is a mystery, and that you can figure out offline on your own. So, where I am trying to go now, this idea we borrowed from manufacturing testing community and applied it on security validation or Trojan detection. And it is a lot of information, but it is the still same information. We need to do rareness analysis no matter what you do, whether it is a rare signal, rare branches, rare events. Branch you can map to event, but whatever, then you have to do fault modeling. Remember, we are going to do apply manufacturing testing technique. Manufacturing testing technique only understand faults, stuck at 0, stuck at 1 and all that stuff. So, whatever you want to solve, you have to map it to their language. You cannot speak in your mother language and expect them to understand. So, to use that tool, why we are using this tool, it will be clear in a moment. So, then you get the fault modeling, and from that fault modeling we can do different kind of stuff. So, this is click activation, this is ATPG version of tarmac click activation, this is ATPG version of Mero, and then you get the test vector and rest of the stuff is same. You do Trojan insertion and checking and testing and all that stuff. So, just to give you an idea what exactly it is trying to do. First of all, remember, we had to, let me go forward the results and I will come back. So, let me go forward and then I will come back and show all of this stuff. Why are you trying to do it? So, this is actually the motivation. So, if you have in this particular example, I do not remember, about 200 signals we had, 200 175 rare signal, and our objective was to kind of do 1000 n detect 1000, that means every rare signal I want to activate 1000 times, that was objective. If you apply Mero, the statistical test pattern generation I talked about by bit flipping, as you can see, some of the rare signal got activated by million times, some of the rare signal actually not visible, it may not be 0, but pretty close to 0 or 1, because those are the dark black lines. But what you really want, which is what achieved by our approach, that most of them are exactly n, nothing more, nothing less. Through manufacturing testing we can actually force it, I am going to show you that force it. I want exactly n to activate it n times each of them. But the other ones, the reason these guys are failing, you are running random test and trying to tune it in different ways, through this way, that way, reinforcement learning. At the end of the day, it is still random test, and you are hoping and praying they will be activated n times. ATPG actually directly it creates exactly n test, give and take it did not become n, we can talk offline what are the minute details, but as you can see it is actually n. So, if you can make it n, then all the statistical guarantees hold, but in real life if some of the rare signals are very high, some of the rare signals are very low, none of them are n, then statistical guarantees will not hold. That is why you will not get 100% Trojan coverage. Any question on this particular idea? Because when you talk about rare signal, do not assume all of them has same rareness quotient. Some of them would be really rare, not 1, some of them could be 0.1. So, if you keep running random tests, the one which is among the rare, not so rare, they will be activated many times, while the one that are extremely rare will be activated significantly less time, and that causes this problem. And this might be a good time to talk about what happened to the diagram. So, same thing for the tarmac, because tarmac you are doing click sampling, and click sampling the basically your number of clicks and all that are supposed to go up, SAT solving time. If you do ATPG, it is controlled. ATPG is kind of linear algorithm, it has its own problems, because it does not talk in anybody else's language, you have to talk its own language, and few other conditions has to hold, certain paths may not be testable by ATPG. But some other point I wanted to highlight is that why is it the Mero paper got 80%, we are showing it is not even getting 10-20%. Why did it get 80%? Because it ran on synthetic benchmarks, or is I will not say synthetic, the open source ISCAS benchmarks, which are kind of toy benchmark. And if you look at their connectivity, that versus AES is also a tiny design. If you look at the connectivity, do you see a difference? What is the difference in layman terms? This is like everybody connected to everybody. Then even if you activated somebody 10 times, your probability of activating few other people together is very high. Although NDetect theoretically failed, but practically it worked. So, it took us some time to figure out why we are doing better, because when you write a paper, you not only have to explain you got result, you have to also explain the other technique did not produce the number that they reported in their paper for new designs. Because if you do not do that, then you are kind of, people may think the other people cheating, or they might think you are cheating. You are not showing their correct result, which is 80-90%. You can't say, oh, they did not run those benchmarks. So, when you drastically show different number, you have to explain why those numbers are different, and this is basically the story. Now, AES is this way, other one could be even sparse. So, basically everybody, key idea is everybody is not connected to everybody. Here pretty much everybody is connected to everybody. So, that is the basically key idea for why certain benchmarks will do well even if NDetect statistical guarantee did not hold. Let me now go back to where I started. So, then the problem that we had to solve, this I basically summarized. Problem we had to solve is every rare signal, let us say signal S, I have to activate it n times, and n you can choose. Typically, as I said, n equal to 1000 is good enough. If you can generate 1000 tests, that can activate it n times. So, therefore, we have to, this the way ATPG is called, you generate the first one, then you generate the n minus 1. But ATPG has a one idiosyncrasy, and that is true even for SAT solver. If you ask the same question, it will give you the same answer. If you ask give me a test, it will give you exactly same test. So, that is not n tests. So, this n time activation has to be by n independent tests. So, when you kind of follow some theory and try to run it, you say why am I not getting the results? It is because theory had that underlying assumption you had n independent tests, right. We thought effectively it happened to us. We generate that test, we got n of them, we did not even check they are exactly same, we got n of them, we ran and nothing happened. Not just we are not better, we are pathetically worse than state of the art. And then they say what did I do wrong, right, everything seems to be perfect, because this is not for the ATPG. If in SAT solver you ask the same condition, it gives you the same. The way you solve that problem, same thing here, same thing in SAT solver. Let us say it gave you a solution A equal to 1 in addition to other variable B equal to 0, C equal to 1, all that stuff, it gave A equal to 1. What you want to then next time you say any question you asked, in addition to that you say A not equal to 1 or A equal to 0 you provide as a constraint. You can pose the question and give a constraint by negating one of the condition in the solution. So, then ATPG would be forced to give you answer not the same one, unless there is no solution. Let us say there are 20 possible solutions, all of them are equal to 1, then of course, this will return null, then you have to try other one. So, there are little bit of that if you do not do it right, but that is the key idea. So, when you are going for n minus 1, now you see why we did not get exact n, because it does not even have an exact n solution for 1000 possible test patterns does not exist. So, every time you negate one of the assignments and you go for it and it gives you a solution. Any questions? And this idea applies everywhere. Any decent people, you ask the same question, it will give you same answer. You have to rephrase your question differently. Now, for click sampling, same idea. Only question is, instead of using a SAT solver to give the assignment, we are asking ATPG to give the assignment. ATPG has its own idiosyncrasies, but it is significantly faster, and specifically the commercial ATPG tool is significantly faster than SAT solvers in solving problem. And another thing you have to understand, the ATPG, this solution because Synopsys adopted this solution in their this one laser fault injection, all of them, because we were actually running on their million line designs, because they are a DPG tool that will run on million line designs. But if you convert into CNF, try to give a SAT solver, you can forget about it. As an academic exercise, as a paper is great. ATPG, as I said, it has a lot of idiosyncrasies, but it actually runs on the full design, any size design it would run.
But how do you map your this rare event thing to ATPG?
Right. So rare event thing is basically, let us say rare event was for a equal to 1, we call it a equal to 1 is nothing but stuck at 0 for a, that is it. So, because ATPG does not understand anything other than stuck at 0, stuck at 1, anything you have, and because it is Boolean, it is much easier. If it was something else, decimal domain, then it might be little more difficult, but it is basically as trivial as this. Same thing for branch coverage, because for branch it could be very complicated. Your branch, if A and B greater than C or whatever it is, this is nothing but a condition. We create a variable x, give that condition and create a knot of that stuck at 0 of that variable x. So, you have to instrument the design, it does not change the functionality of the design, and then we have a stuck at 0 on that element. That is what we ask the ATPG tool, do a stuck at 0 on that. So, then ATPG will give you the solution. Any questions? Now, any of you want to go home today and want to solve it, you have Synopsys design compiler and Tetramax. This is the exact setup. This is the exact setup. You take your design and hierarchy, you write the file, you get all the different kind of library, you get still file, all that design rule check you do, and then you feed that to Tetramax and you get the test vectors. It is basically in the script we are basically putting that constraint in the basically still file. Whatever solution it gave, we parse it, put one of them as a negation, we put it back in. So, it would all work. Now, kind of to summarize what we talked about, so on one hand the statistical generation is basically trying to activate each node at a time and hope and pray that the trigger, which is some number of nodes, that gets activated. And on the other extreme, and this one is, or maybe the animation did not appear. So, basically when you do one at a time, this one activates, these two, maybe this, when you are activating n times, it was trying different combination. On the other extreme, you try to activate all of them or the click, and then hope, not hope, that basically the trigger would be activated, and this we talked about already. These results we talked about already, why if you do blindly statistical, why it would not work, and this scalability I talked about for click covering. Now, we are going to basically use explainable AI with Shapley ensemble boosting. We briefly talked about Shapley value analysis, and if you recall, explainable AI, there are many algorithms. Decision tree is one of the simplest one to understand, but its not accuracy is not great. On the other hand, Shapley and Shapley values or integrated gradients, they are, or even many of variation of large language model, they are explainable, but they could be expensive in terms of size, cost, running time, so on and so forth. So, before I begin, let me just quick recap. So, what do we do in machine learning? We have a raw data set, we kind of choose which features to use, then machine learning model, when we train, it kind of finds a boundary, cat or dog or whatever it is, and then in real, so this is the training time. In the testing time, we are basically asking it interesting questions, showing a picture and asking, is it a cat, is it a dog, it classifies. That is the key idea, and nobody cares about training time in general, but people care about when an unknown object, not necessarily unknown, the objects that are not seen during training time, how are you doing with those objects? What is your accuracy? What is your false positive, false negative? That is all people matter. Now, normal world, there is no guideline for feature selection. Before explainable AI came in about 5-8 years ago, people were basically, it was acceptable in a paper, you just say well, in fact I have shown few of the features before, I will show few features. Here are the features we used, as long as that is reproducible nobody will object. How did you come to this feature 5, 6 of them, why does it work, nobody will ask those questions in those days. These days people would probably ask, but there is no guideline here. Shapley value analysis helps you in that, you exactly know which feature is helpful, which feature is not, so you can rank order them. So, similarly, the training cost and model complexity is very bulky, something does not work, you keep running few more training, you do not know why you are doing, it is like your kid is not doing well in the exam, you are waking up the kid at 4 am or making the kid study until 4 am. So, all of them are basically without any objective functions, you are assuming making a kid work really harder and longer hours is basically a great idea. So, in ensemble boosting I am going to talk about where basically you put less effort, you get better accuracy, and that is why the name was Trojan detection using Shapley, that is that, and ensemble boosting this one. These two we will talk about together. And then the existing stories can provide model without any interpretability, but Shapley value analysis can provide you that. Now, here is the detailed algorithm, I am not going to bore you with the algorithm, but I want to just say you it has all the portions of a typical machine learning algorithm. You have data sampling, training, weight adjustment and feature, then ensemble prediction. Let me pictorially show you. Before I do that, I wanted to show you the features. Even for Shapley value analysis, you have to give some features initially. Even in fact, even in reinforcement learning we did give it, you did not probably realize when we say scope and controllability, observability, those are the features. Rareness, controllability and observability, those are the features for reinforcement learning. And here because it is a hardware design, this is number of signals or nets, number of cells or gates, fan in, how many fan in it has. So, fan in, if this is an AND gate, so fan in basically this is a 3, you might think it is a 3, but the way fan in is it is coming from some, it is coming from, I have to escape, what did I do? So, this is coming from another logic and this was called fan out because it is going to other logic. If this is going to 2 other gate, we call it a fan out of 2. If it is coming from 3 other places, fan in on 3. So, same thing fan in, number of flip flop and multiplexer and what not, lot of parameters, that is basically the features. And if you want to feel more comfortable with features, remember in decision tree we are trying to do, if we are trying to do Trojan detection using decision tree, I showed you other example with malware detection, it would probably something like this. So, feature 1 is more important and then feature 2 would be number of cells, feature 3 would be number of switches, and based on certain decision you call somebody Trojan free, we call somebody Trojan infected. Can anybody tell me where did I get all the rare switches is fine, it makes sense. Where did I get this greater than 200, why not some other number? How did I get that number?
Was it because of the entropy and Gini index?
Remember decision tree is also a machine learning model, you need to do training and during training I will give you all the information, I will give you benchmark, I will say it is Trojan inserted. You look at that manually or through the machine learning model whatever it is and you keep observe all of them where you going through, all of them rare switches is greater than number of rare switches based on some threshold greater than 200. Of course, you realize if my training set was different there could have been one Trojan inserted where rare switching is less than 200, it is possible, then you have to change this, and that is one of the reason this is kind of easy to understand, but not a great machine learning or explainable AI model. But all of these numbers, all of these conditions got generated after going through the training process, whether you are going through manually, you looked at all the designs or you ran it and decision tree actually figured it out, whichever it is that is what it is. But the good part is if it describes somebody as Trojan inserted, you can walk back and you can explain why I took this design, called it Trojan inserted, and if it is wrong then it is probably one of the condition was wrong that it needs to modify. explainability gives you that insight. Instead of a black box where you just give some design and it say it is Trojan inserted and you ask why, how did you figure that out, you have no idea. Now, how does ensemble boosting work? So, that is the explainability part. Ensemble boosting, the way it work, let us say I can't afford large language model, I do not want to use large language model, then I will use whatever model I have. In fact, decision tree will work here for ensemble boosting. In fact, this work was done using Shapley plus decision tree. So, you run the decision tree and as we expected, result is not going to be good, it is going to make a lot of mistakes. So, then I know the mistakes, what mistakes it made. I put another decision tree whose job is to just fix those mistakes made by the first one. First one I might have trained 3 months on, I am just putting some number, let us say 300 benchmarks I ran, whether 3 months. No, but the error it made on 100 of them. This model I am going to train with 100 benchmark where it made the mistake. It does not know the other 200 or it is making correct. So, model 2 is not more powerful than model 1. I want you to understand that. Model 2 is, if you ask model 1, model 2 is good at capturing the error of model 1, that is it. And it might still make mistake, and let us say out of those 100 it probably did let us say 90 of them correctly, maybe it is still left with I do not know, just 9 of them is still left and made mistake, and it can continue until we basically have 0 left. That is the whole idea. Assumption is it would converge, otherwise Shapley. So, this is basically the idea of boosting, and then idea of ensemble, and once you have n of them, then you take the ensembled output. So, the final result is some combination of these results, because each model is not stronger than the other. This is not the final answer. Final answer is some combination of, some weighted combination of this one plus this one plus this one plus this one plus this one. It is quite possible this one may have higher weight, this one may have lower weight, but it again depends on tuning and all that stuff. But each of the model is very small, think of a decision tree, and because this is the training time, you can spend as much time as you want. During run time, all of them are running in parallel. When you give a new scenario, all of them runs in parallel, and then that parallel run basically it produces the result, and that is significantly faster. That is why it is called boosting. This is ensemble of models, and the idea of, because some simple model, lot of simple model runs in parallel, that gives you the speed up, that is why it is called ensemble boosting. Boosting is the speed, ensemble is one helping the other. Any question on this idea before I put these two ideas together to solve the Trojan detection? Okay. So, interpretation we briefly talked about earlier, that normally training, when you do ML model, you have original model, and in any interpretable model creates another model. It may not be in parallel, it may be merged together, but conceptually we can view it as parallel, and it may do lot of things. For Shapley value analysis, all it tries to figure out which of the features are more powerful, can I rank the features, that is the visibility it gives. Shapley value analysis does not give the visibility like a decision tree. Decision tree gives the full visibility. Shapley value analysis, only visibility you get, ranking of features, that is all you get. So, with that, and just to recap, how did Shapley value analysis work? Basically it creates a competition of, so it computes the contribution of different feature through a competition. If there are 3 features, to find out how much one is contributing, it is doing 1, 2, 3 working together versus only 2, 3 working together, and subtracting that result or gain in a competition, and they do average of all these scenarios, that is basically contribution of 1. They have to do same thing for 2, same thing for 3, and when you have a lot of features, it is going to take a lot of time, but this is actually in the still training time. and if you want to see pictorially, you have a lot of data. In this particular case, these were all of the benchmarks, think of Verilog benchmarks, and you are trying to figure out do they have Trojan or they do not have Trojan, and these are the initial some features, name is not important, and then you run that disease entry. Remember, you are trying to do ensemble, you run that disease entry. Now, it might be a confusion, wait a minute, disease entry and explainable AI model, Shapley value analysis and explainable AI model. In this work we combine both. Shapley analysis is only Shapley, disease entry is giving ensemble. We wanted to do this Shapley ensemble boosting, we came up with this term, no term existed. So, then we do Shapley analysis when this decision is happening, Shapley analysis, and we are doing weight adjustment, because in this example what we are seeing is, so black dots are unseen sample, they have not been analyzed yet. The green dots are correct prediction it made, whether it is Trojan or not Trojan does not matter, it made correct prediction. Red ones are the mistake it made. So, then when I, and then Shapley analysis is doing the which of the feature are top, which of the feature are bottom, it ranked them, top ones are higher ranked, bottom ones are lower ranked. So, for example, whatever the name is, this is higher ranked, this is lower than that. And then we run another disease entry and continues, and the assumption is now it made 2 error, this should have 1 error, this will have no error, right, and it kind of different features, different type of features. So, red one is high impact feature, blue one is low impact feature. So, that thing kept changing, this different one became high and low impact. So, that is basically the whole story, and that will give you the final ensemble prediction whether you have a Trojan or you do not have a Trojan. Any question on this idea of Shapley ensemble boosting? You start with a set of benchmarks, you run, you make some mistake, put somebody just to fix those mistakes, and this is during the training time, all of it during training time. It may take a long time, but once this is done, then basically you simply run, you give a design and all of the model runs in parallel on that design to produce a result. Same produce a Boolean output. This is a classification example I talked about. You could do similar stuff with regression also.
Sir, this is same like random forest or like it is different?
No, this is not a random forest, because each stage we are using only one tree. We could solve that problem using random forest. Instead of one decision tree, we could use a random forest right here.
So, like in random forest, we take lots of tree and then use, and the output of each all that tree we combine.
Right,
so
absolutely. But all I am saying is, if you want to do random forest, visualize this single tree as the random forest in itself. Each stage a set of random forest, and then eventually we are going to decide something. If you want to use this Shapley ensemble boosting idea,
okay,
we could have done that. And your idea is well taken, that why are we doing all this stuff instead of Shapley? We could have done random forest. Absolutely, you can try that and try to beat this result, then that is going to be a paper. Any other questions or comments? So, now anytime you do any work, you have to show a lot of results, and now that we are diving into deep into AI, most reviewers want to see all of these accuracy. Of course, everybody want to see, but they want to see precision, all these names. Let me spell it out. So, true positive, true negative, false positive, false negative. True positive is that when it says it is Trojan free, that is indeed Trojan free. When it says Trojan inserted, it is indeed Trojan inserted, and false positive, false negative is inverse. You want the accuracy is all of the decision, and on top is true positive and true negative, correct decision by all decision, that is your accuracy. And similarly, there are recall, F1 score, and many such numbers, and each has its own interpretation, people are interested. And when you kind of compare, so this one is random forest, then CNN, this is reinforcement learning we talked about earlier, the reinforcement learn test generation using reinforcement learning, which is flipping the bits using reinforcement learning, and this one is Shapley ensemble boosting. And basically you want to show accuracy is high, and you also want to show, there is a lot of numbers I am going to skip, but basically you want to show that accuracy is high and your time time taken to do whether training, whether to testing, all of them are low. That is what you want to show. But what is the important part, the explainability part, I want to just zoom in little bit. So, for each design based on certain number, every design has a kind of a interesting number. For this particular benchmark EFX is 2.192. So, if your final feature value, think of for AI model, this is the line. Remember when any AI model we give, what does it do? All these points they learn, they kind of create a line. Let us say it is a vertical line 2.192. If final story is on the left of something, then it is basically Trojan free. If it is on the right of something, so this is Trojan free and this is basically Trojan inserted. So, this is basically Trojan. So, that is the 2.192 line. Now, how ML model gets that line, we can talk offline, but basically now that we have that line, what are these features doing? Every feature is like doing a tug of war, it is pulling in a direction. So, for example, I am going in reverse direction, out of these 3, 4, 5, 6, 7, out of these 8 features. So, the bottom one output flip flop, that is pulling to the left by very tiny margin, saying I believe it is Trojan free, and wherever it stops, that is where the next one starts, not on that line, and it say no, I do not agree with you, I think it is a Trojan insert, and then it try to pull that direction. Wherever this stop, that is where this one starts and say I do not agree with you, and this one says I do agree with you. So, this forward backward later, when all the features are done, question is where is the final line, and is that on the left of 2.192 or right of it. If it is to the left, now how is it, how this Shapley analysis different from normal machine learning? Normal machine learning, knowingly unknowingly they are doing similar stuff, some stuff, eventually they are coming at one point. They are also use a notion of marker, either you are on this side of the marker or that side of the marker, this side of the plane or that side of the plane, right. So, this particular, and same thing if you see another design. So, or another same design with Trojan inserted, it started with here everybody pulling pushing later, final result is on the right of that line. So, this is basically then this is Trojan free, that one is Trojan implanted. Any question how explainability? Now, how is, so this is basic, this information Shapley analysis will give you. What do you want to do with it? Let us say you gave a new design and it made a wrong prediction, then you know whoever you made highest priority, who pulled the maximum, because 2 people pulled the maximum on this direction. If this design happened to be Trojan inserted, you want to reward the people who tried to pull on the right direction. Specifically this dude, it tried so hard, Nets tried so hard to convince everybody it is Trojan inserted, but these 2 people tried so hard to pull it back. So, you want to penalize these 2 people and push it down in the priority, in the ranking. You want to promote this particular one up. Now, it should not be a brainer that the 2 people who are doing on the top in the story is rare switches and dynamic power, because rareness is the bread and butter of Trojans. So, even before AI explainability you could have predicted it, but when you are trying to apply explainability on new domains where you do not have enough insight, it will tell you that, and then you can say, oh, that makes sense, that makes sense. Same thing for dynamic power, because it involves switching, which I will come in a moment. Any question? Now, when you do multiple benchmarks, story would be different, but nonetheless they will collectively, all these things will pull you. There I zoomed into one circuit, here 10 circuits, some circuits are pulling towards left, some are pulling towards right. The one going towards left are Trojan free, the one going towards right are Trojan inserted. So, one thing I wanted to show you, robustness, and this is another aspect any reviewer would want to see. What is the robustness in this context? Robustness in that context is if you go for different trial, how stable your solution is. Here robustness means something else, and which is, if you are saying something is Trojan free based on certain feature, attacker knows that, attackers try to play with it. They want to bypass that, that is known as adversarial. We remember adversarial machine learning, where a stop sign would look like a yield sign, all that we talked about. If somebody do that, you see random forest from 75% accuracy, it went down to 44%. 44% is like random guess, as bad as random guess. 88% it went to 33, very bad. So, TGRL also went very bad, even supply ensemble listing went very bad, but the important part now to observe, it is all become bad as a random guess. What is important when you retrain it? Anybody knows how to do retraining? For a kid example, retraining is make the kid study even harder. That might be the reason kid is doing bad, put more pressure on it. That is the retraining happened in situation like this, where you do not have explainability, although that is technically not correct, it improved, it went very close to original result when you do retraining, even this one also went very close to this one. So, TGR, the reinforcement learning one went up, the supply ensemble went really up. So, the retraining time explainability gives you an advantage, which is you exactly know why things went wrong. So, when you retrain with a data set, images, whatever made a mistake. If there is a cat which has a ear like a dog, you want to just put few more training samples, where the cat you label that example that looks like a dog as a cat and train it. So, retraining is a great idea, but during retraining time you have to give guiding examples, right examples. If you give too many examples, that overfitting problem. If you give wrong example, you are going to do even worse, but none of them actually become worse. But the key idea people want to see, adversarial story will happen, how quickly you can recover and give good results, that one aspect people look at. Second aspect people look at, how much time do you need for retraining. I believe this is in seconds or minutes, I did not remember, but the thing is how much time do you need. So, the reinforcement learning took most of the time, a lot of time, because of the learning agent and all that stuff, and SAPLI took very little time. So, now I am going to start talking about Trojan detection using something orthogonal approach. This may be a logical time to take a break. Do you think we should do? Let us take a break. After the break, we will talk about Trojan detection using sidechain analysis.
How long
I am actually done with the slides. That is your call.
So, side is speaking a lot, right? So, maybe 20 minutes will take 15 to 20 minutes.
Ask them how much time they need.
Sorry, you need break, not us. So, 15 minutes and then depends on side. 2:30 will come back. Then
না কিন্তু এটা তো ট্রোজান ডিটেকশন হচ্ছে সবগুলো বলবো। down. Where did it go down? Good afternoon. Now we are going to talk about Trojan detection using side channel analysis, and Dr. Karfa talked in detail about side channel analysis and attacks. Just to recap, that when you do side channel analysis, there are different types of side channel footprint. So, this example we are using a power footprint. Instead of tracking the power, if you are holding a probe, it could be electromagnetic emanation footprint. In few minutes, I am going to talk about path delay footprint, but whatever it is, we are not looking at the functionality of the device, we are looking at side channel footprint. And if some computation is going on, if you can connect your supply and observe the power dissipation and plot it, you would be able to figure out what computation is going on. Using machine learning, if you kind of trained your machine learning model for different programs and different footprint, it would be able to detect what program is it. Now, in general, the basic idea, as you already know, depending on each operation in a computation takes different amount of power. It could be just a square root operation, this could be squaring and multiplication. So, you can analyze this simple thing, and when this idea first came in, basically first attack was all smart card was kind of broken the security of it. Of course, this is simple power attack. These days attackers also smart enough, they do not want to keep this footprint, they will either make this one bigger or that one smaller, but whatever it is, you can do differential power attack and many sophisticated techniques, and this is power based side channel attack, power or dynamic current based. Now, we are going to use those features to Trojan detection. So, I am not going to get into the detail of side channel aspect of it, rather I am going to focus how do we use those side channel features for kind of Trojan detection. Let us start with the dynamic current or power based, but before I go there, I wanted to show you that whatever I shown so far earlier, the statistical test generation, whether machine learning, whether direct or not direct, we call it logic testing or simulation based security validation, and side channel. If you can look at side by side from a Trojan perspective, the positive aspect or most of the aspect of simulation based security validation happens to be the negative aspect of side channel and vice versa. Whatever is positive of side channel happens to be the negative. So, this simple observation essentially led to the work that I am going to talk about, that you can combine them effectively to kind of take advantages of them, and this is a common research theme. You kind of understand two good ideas and you can put them together. So, let us touch upon one of them, what is logic testing. So, even if you have very tiny Trojan or tiny Trojan, what does that mean? Let us say trigger of only 2 gates, we call them a tiny Trojan. So, for logic testing it is a great idea, because activating a trigger of 2 is much easier than activating a trigger of 10, because the probability of activating is 1/4. Probability if you have like 10 or 20, it is like 1/2 to the power 10, that is very low probability. In contrast, in side channel it is negative problem, because one tiny AND gate with 2 input, the extra power it would consume or dissipate, that is just negligible, not even nanowatt, even like less than that. In a bigger scheme of things, when things are taking milliwatt or watt, in a tiny nanowatt of power difference will not show up, and specifically because of the process noise or process variation we talked about, that could be anywhere between 1 to 10%, let us just say 1 to 2%. That would be still in the milliwatt range. So, a nanowatt will hide easily. In contrast, if you give a big AND gate, lot of inputs, it is a problem for logic testing, serious problem, because the probability of activating goes down by 1/2 to the power n, but large one is an advantage for side channel. If there is a big gate or a lot of gates sitting there, they are going to consume or dissipate a lot of power, and if you are measuring power, you will see the difference. Any questions of how positive and negative kind of map each other? So, side channel analysis is bothered by process variation, because process variation affects side channel. Logic testing does not care about process variation, it only cares about the final output, that is all it cares about. So, if I want to pictorially present it, the test generation problem with testing, you apply some test vector. How do you generate that, how quickly you get good test? We talked about lot of algorithms, whether ATPG, reinforcement learning, Shapley ensemble boosting, how do you get this number and flip the bits, that is different. But once you do that, if you have a golden design, original or Trojan injected design, then if there is a difference, then you know Trojan got activated. But we know the real problem. Real problem is how do we get to that number that would activate the Trojan, because the input space or the test space, this space is exponential. The number of inputs that you have to try is exponential. In contrast, in side channel, we actually do not care about the input space. If you recall, when we talked about simulation versus formal verification, we had this same dilemma. Here, sure, you apply something, but it is really not really important what you apply. What is important that you do a diff of the power signature that is coming in, and if that power signature has some difference which is beyond process noise, then it is good. But the problem we know, because number of gates are so small, the difference of power even in the most expensive oscilloscope with amplification, there is no way you can find it in reality. So, then what can we do? We can combine both of them. We can use the efficient test generation, do the logic testing, and then we can do side channel analysis. So, input is logic testing, output is side channel analysis. So, what is the key idea? Key idea is we want to maximize switching in the suspicious area and minimize switching the rest of the design, that is the key idea. Again this same thing, it relies on the threat model. Let us look at an animation to understand what is going on. So, let us say we kind of computed our error signal, these red dots are error signal, blue dots are actual design. In reality, number of red dots would be in small 4, 10, that range, number of blue dots would be in millions, here it is not proportional. So, when you apply any input, first of all we do not know whether there is a Trojan, we also do not know where the Trojan is. In this case, let us say I told you there is an AND gate sitting here that is taking this one and that is the trigger, that is the Trojan. So, if at any test case can activate these two, then that is wonderful story, right. So, let us just run a test case. So, it just coincidentally in this test case both the red dots are flipping, switching, that is great. Switching basically means it is going to charge the capacitor, it is going to consume the power or dissipate the power, our power analysis technique will be able to detect it, but the problem is other millions of blue dots also switching. So, 2 red dot switching will easily hide with millions of switching, is that true? Let us plot the data. So, this is again a silly benchmark from ISCA's benchmark suite. Even in that silly benchmark, I can illustrate you this problem. So, the amount of switching of the rare gates or the we call delta switching, that is basically is the this particular is basically this particular line. As you can see that when you do random versus n detect for higher n, the switching indeed increase, which is good, switching is increasing. But what is not good, look at that red one, and by the way this red one is not this dimension, it is this one total switching dimension, which this number is significantly larger. In this tiny silly example, it is about 10 times larger, 10 to 20. In general, this is going to be 100 to 1000 times larger. And what you observe, the switching of the main design, is also increases. If it was on the same scale, maybe this is still fine, comparable, but because this is a 10 times or in this example 20 times larger, in reality 100 to 1000 times larger. This tiny increase, no matter how it looks, it increases from 10 to 17.5 in power consumption or power dissipation, is meaningless compared to these large scale of things. So, both are increasing, both are switching. So, it is not. So, sensitivity, the term that is used in Trojan detection is known as sensitivity, and in layman terms there is a formal definition to it. In layman terms is basically rare switching or switching off rare nodes or rare events divided by overall switching. And because rare switching is so tiny or overall switching is so large, this number is negligible. And this sensitivity is important because the device you are connecting for measuring, that device should have sensitivity to capture that. Any questions? So, then now it just turns out in that work we are able to reorder certain tests without knowing why it worked. It did work, which is analogically this Trojan circuitry signals flipped, and also some of the original design signal flipped. Now, in reality you realize this picture is not possible, because from somebody to go from input to output, it needs to create event in at least one of the path. Here, as if I am showing there is no activity in anywhere in the design except in that region, that cannot happen. It is going to have some activity on some path. It is basically the idea is you maximize switching in the rare or suspicious region, whatever your definition of suspicious. For Trojans it is basically rare nodes, that is one objective, and another objective is minimize switching in rest of the circuit. So, you select the or generate the test cases so that you minimize the switching basically in the design. Overall design you minimize it, suspicious area you maximize it, so that it become easier. So, in this particular case we can have an effect like this with certain kind of parameter. You can have the overall dissipation actually went down and the delta switching went up. If you can somehow able to locate this region and measure at that time, then Trojan detection becomes easier.
How conceptually it is possible to do that?
So, conceptually it is possible because you are, so first of all theoretically it is possible, practically for ISCAS benchmarks it is possible, real design we do not know. It is possible because you are trying to find the path where you can go wherever the rare nodes are. So, while you are going to this cone, you are trying to not disturb too many paths of the cone, you are trying to create switching only the few gates in that cone, and then that would create switching. So, there has to be a test pattern which is able to do that. So, the idea of the algorithm is to find such a test pattern.
But you have to give input to the other inputs also.
You have to give input to everything, but the thing is you want to give input that will not change the ones that are not needed for switching there. You want to choose input such that those gates do not switch. Inputs you still have to give, but it is just that think about it the way, if I want to do a controllability problem this way, you are basically trying to figure out what is the minimal changes I can do in the path to have that switching possible. That is basically the objective function.
Now, how do you identify that?
Identify which one?
Which are the so you just take the cone of influence and how do you identify the minimum test case?
Right. So, we have some improvement on that. In this particular paper we are basically trying to start with two pair of pattern and choose the pair that have that objective function. Later we kind of improved it, but basic idea remains the same. How do you play this minimize maximize game? Two sets of elements, one has large set, another is small set. You are maximizing in a small set, minimizing in the large set at the same time. That is basically the objective. And genetic algorithm is a natural fit, machine learning is a natural fit. I will talk about both of them. So, it is basically you are trying to create minimal switching so that you can create the switch with two vector. Unlike the Trojan detection work, we are only talking about one vector. For power switching you need a test case is a pair of vector, because a pair introduces switching. So, you have to find the first and second pair, but the problem of this one is the noise margin is really small. No matter how much you switch, the path is still long. So, how do we improve it? In our subsequent work, we basically looked at that first vector is important, but the second vector is more important. So, once you know the first vector, how do you do second vector? In the initial work, we kind of looked at reordering and we got to the right answer, but why that was right answer we did not know. So, instead in genetic algorithm, we are basically saying if this is my first vector, then what would be the second vector that has that objective of minimize suspicious, minimize design switching and maximize suspicious switching, and then that is basically going to do the trick. And the reason it worked, and initially we are kind of bothered why is it working. Initial reason it worked, although you have 200 inputs, once you know who are the rare ones, machine learning, in fact machine learning works like a charm here, and later we realized how did machine learning do better than anything else. Machine learning very quickly figures out which rare node is kind of correlated which of the input. It is like everybody is not equally correlated, they have we call it input affinity. So, which of the input has affinity to, and a minor change in input, actually if they have affinity, minor change in input will create maximum change in their switching behavior. And so, basically this is kind of an ideal problem for machine learning. For us it is kind of difficult, you trial and error, they quickly figure out, if you run few test cases, provide certain things, very quickly they figure out who is kind of have design has affinity. And because these designs are not random, they are written by people, there is some structure in it. That is why it works. If somebody came up with a random design, all these algorithms will not work, machine learning will not work, even genetic algorithm will not work. So, those are the two basically core observation, and the way genetic algorithm worked here is basically you start, once you are given the first pattern, initial input pattern, now you are trying to find the second pattern. In this example, we are trying to flip one of the bit. So, there are 5 bits. So, one of them we decided to keep the same. So, we are basically trying different choices first generation, and then you are computing fitness with respect to the objective, and then you again try some mutation, selection, crossover, and do the iteration to see if you can improve over the thing, and then eventually when you are not able to improve anymore, you say you know what, this is my first test case pattern, this is the pair that I am interested in. That is basically the idea of maximizing switching through current analysis. Now, does it improve sensitivity compared to if you just do some ordering and try to do that? It definitely does. Now, here is the another thing again, when you look at another paper, it just happens to be both our paper. When you look at another paper and that kind of showed you certain number of results, and you want to show no, that is not good, then you have to say which sensitivity is measurable by oscilloscope today. Is it 10%, is it 5%, is it 2%? If like close to 1% sensitivity is measurable, 1% or less than that, then the existing work will still be able to detect Trojan. But if today's oscilloscopes are not able to do that, then basically you can safely say unless your Trojan sensitivity let us say higher than 10, existing approaches will fail. So, which one will say it has to be realistically based on what oscilloscopes are on the market, what sensitivity or what difference they can measure. Now, I am going to talk about another side channel footprint called path delay. So, path delay is basically, if you look at this sequence of gate, they are going to consume some delay. So, depending on when you apply the input and when that output would be observed, in this particular case this gate is going to take this much of time, the second gate is going to take that much of time, and so on and so forth. You can kind of figure out which gate will take how much. So, that is the notion of delay. You apply an input and that change how long it will take to reach there, and this delay itself we can kind of utilized to do Trojan detection. And I will go straight to the point. How do I do that? So, let us say this is your original golden design, this is a Trojan inserted design, and as you can see this trigger is coming from somewhere, this is your payload. Now, if trigger is not activated, then the delay difference is the delay difference of a gate only. Whatever is the delay is the time, propagation time of all the gates and wires in that path. Because of Trojan insertion, only difference is this XOR gate, that is it, and that too if trigger is not activated, then it is going to go through the normal functionality, and one gate difference is in the picosecond difference. In a bigger scheme of things, that cannot be detected by anybody, but if we can somehow activate the trigger, then not only there is a single gate, there could be lot more gates. In the payload there could be lot more gates, in the trigger there is a lot more gates. This path is totally different than this path. That does not mean delay would be more, it could be delay could be less, but it is a totally different path. Now, you have two different paths, that is why there is a two different delay. When you apply the input, when you measure the output, there is a delay. So, the delay difference will help you in identify the Trojan. Now, this problem could become complicated, because if you recall, in a normal design with process variation, even the critical path sometimes take longer, sometimes is shorter. As long as this delay difference is higher than that process variation, then or sensitivity, then it is a good idea. Any question on path delay based analysis? Now, this idea of delay people use left and right in for side chain analysis for different kind of delay. Even if you recall, when I talked about cache timing attack, I have a whole day of microarchitectural attack. The cache timing attack, one of them, that is also based on this idea of delay. You access a data, does it take short time or long time? Based on that, you figure out who accessed it, then you figure out what value is it. So, you figure out the value of somebody else based on the delay. So, idea of delay, as I said, in almost every domain, and the delay based analysis like power based analysis is very stable, and because the gates and paths, all these are kind of interestingly independent different path, you can actually measure them parallel, and there is a lot of work on delay based analysis. So, I am going to skip all the content of how all of these works. I am going to spend some time on machine learning. So, the last three work of today are all based on AI and machine learning. What I want to do, show this delay based analysis, how do we apply machine learning on it? We know what is delay. There are publications on how do you do delay based Trojan detection, how do you apply reinforcement learning, and as you can see, this diagram we have seen before. Only difference is, instead of scope parameter or rare values, this is delay difference, everything is exactly same up to the point the flipping the bits. Up to the point flipping the bits, everything is exactly the same as statistical tests, only thing is the delay difference is. So, the mechanism to measure, now those of you who work in this area, you know you can control the clock, and you can control the clock and you can create two different delay. If you can control the clock, you can create two different delay, you can measure the delay very effectively, very easy actually measurement of delay. But if you cannot control the clock or change the clock duration, then delay measurement is difficult. Any question on reinforcement learning? As I said, it is exactly same, only thing changed is the delay difference.
One question, sir.
Go ahead.
What is the reward function for this?
So, it is same thing, do I keep the flip, do I ignore the flip? It is the same function. You can, on top of it you can do genetic algorithm, but I am saying the core idea of reward penalty, it is exact same story.
But if you have, say, how do you get two version of the design, because to get the delay difference you need two version of the design, right? But
all of these works, very interesting question, how do I get to, all of the work I have talked about so far is about we have the availability of golden design, we know how much delay it is supposed to take. In reality that is a problem, that is why I will talk about one work on golden free detection, actually maybe I will talk about two works, but all of them based on that the golden model is available, you know what should have been the delay, what should have been the output value, so that when you run this the output value is different. And again any test cases you run, whether the delay or not delay, you basically want to show for different design what is your Trojan detection rate. So, in this particular case reinforcement learning is able to get closer to kind of 80%, whereas many others when the design size increases, I know all of those are silly designs anyway, even within themselves they are increasing order. This is like about 10,000 gates. So, even the existing approaches kind of accuracy goes down pretty drastically for delay based analysis. Now, I want to talk about golden free Trojan detection. So, there are two techniques I want to talk about, and I am going to talk about zero shot learning. Maybe another technique, let me just create a W here. Another technique I am going to just write it here. So, golden free Trojan detection is the real world problem. In fact, DARPA, defense, most companies they say we have only one model. Although initially they started with a golden model, nobody kept track of it, and nobody started adding the features, either customer requested or something happened last minute, all that stuff. Nobody had time to go back and modify the original C model, Verilog VHDL model, nobody had time to do that. So, therefore, there is no golden model even for functionality. Nobody has a golden model, people have only one model, whether the soft version like VHDL Verilog or fabricated version of a chip, they have exactly one. In that case, that is called golden free Trojan detection. What do you do? So, there are a couple of ideas. I am going to just talk about two. One is on self referencing, that I am going to talk about right now, and then there are tons of work on machine learning model. I will show one work on zero shot learning. In fact, machine learning is kind of used extensively in most domains when you do not have a golden reference model, because then you are kind of. So, people want to go for, if you recall we talked about known known, known unknowns. Let me write that once for you and then I will come back. Known knowns, known unknowns, known knowns, known unknowns. Let us just put one of them, unknown, unknown. So, known knowns in the Trojan example, think of, so this is a Trojan, let me take another color. So, this, think of this as this is a Trojan and this is a 4 trigger. It is just that during your training time, the examples, the 4 signals you took as a trigger is different, and during testing time the 4 signals you are taking as a trigger is different, but it is both are known. Trigger is also known, that is, we are talking about a vulnerability called Trojan, that is also known. Known unknown would be, it is still a Trojan, and again how much unknown you want to introduce, that is different. I am just saying it could be 6 trigger, it could be 8 trigger, the situation, these situations were not included as part of the training process, that is why you call it a unknown. There is an unknown parameter to this story. Unknown would be, I mean it cannot be Trojan, right, it has to be something else, I do not know, whatever that is, you think of that, and this also has to be think of that kind of stuff. So, most people are targeting AI for these two, and most companies and most countries are interested in this one. And their objective is, can you do natural language processing, read today's newspaper, tomorrow's newspaper, day after tomorrow's newspaper, and can you predict what attack is going to happen. Maybe news is not in the explicit form, maybe for human to read news all across the world is not possible, but a machine learning will read that, make some unknown dots, connect some unseen dots, that this is happening in Russia, that is happening in Iran, this is happening in India. So, I guess this is something is likely to happen. This seems to be matching something happened 30 years ago in a country Y. So, whatever it is, that is basically people, and this is completely AI territory. Although I am taking only example of Trojan, but that is the key idea that you want to go after. Now, let me talk about self referencing for a moment. if I do W, would it let us do self referencing here. So, in self reference now if I do I have to let me try the another. So, the idea of self referencing is when you do not have a golden model, can you compare with yourself, you yesterday versus you today. You do not compare with anybody, you do not get stressed in life. How did you do yesterday, how did you do today, that is the closest analogy. But in real life, think of a processor, you are doing Trojan detection in a processor, right, and processor has two ALU, ALU 1 and ALU 2. Now, the idea is you generate test pattern in such a way, so that it applies to ALU 1, it applies to ALU 2 and you compare the output. I always use exclusive gate to just say, but you just dump the value and compare, whether it is a functional value, whether it is a power side channel, delay, whatever it is, that is what you try to do. That is the basic idea. Of course, there are lot of intricate details and question. For example, if you take any real world processor, you try forcing on ALU 1, it will work. You try forcing on ALU 2, it will not work, because if ALU 1 is free and not hot, the instruction you cannot push to ALU 2 from the external port I am talking about, because the internal logic is that way. The if then else statement somebody wrote that way, you cannot bypass it. So, there are practical limitations, but the key idea is if there are self similar components, self similar functionality at whatever granularity level, can we create test patterns, so that we activate those self similar components and compare their output in some form. So, that is one line of work. Then the line of work I am going to talk about is zero shot learning, and it uses that advantage of zero shot learning. What is the zero shot learning, anybody remember? Machine learning, you train and test patterns, or the thing you test in real world has to be similar to the things it has seen during training. If it is different, you trained with horses and asking for zebra, it is not going to work, right. Anybody remember what is one shot learning? You train for a long time, but you are asked to apply in a domain where you will be given an hour, a day, not same amount of time as before. Can you provide enough information quickly, so that it kind of work? And the idea of zero shot learning is you train in a domain, in this case it happens to be animal, it does not have to be animal, and then you take that model, put it in another domain, you would not be given any opportunity to train, not even 1 hour. How would you perform in that domain? And zero shot learning claims is I will perform as good as if I was trained in that domain. How does it work? I will give you that insight. I talked earlier today in the Trojan context, I will give you the insight, but zero shot learning is I do not need to train. I know I have been to Japan, been to Korea, I am going to go to France, I do not need that, no learn that language, I can manage, right. So, that is the idea. So, how does it work for Trojan detection? Remember, we are trying to still achieve golden free using zero shot learning. So, before that, if you recall, we talked about supervised learning. Supervised learning, you provide test cases, you provide label during training time, machine learning builds a separator, then you give a design which may or may not have Trojan, and you are asking is it Trojan infected or is it clean. So, it is able to detect, that is supervised. Unsupervised, you are basically some kind of distance metric, either you are with me, my friend, or you are my enemy, some kind of circle gets created, either you are in that circle or you are outside the circle. If that notion, you do not need any training, you do not need any label, actually I am flawed, you need training, but it is just that you do not need label data, it just kind of figures out which are similar. And once it figures out, it kind of then you give a test token, is it inside the circle or is it outside the circle. So, that is basically unsupervised learning. So, what we are basically trying to do here is a combination of them. By the way, the zero shot learning idea is a well known idea, it is there at least 10 years if not more, actually more than 10 years. So, the idea here is that we pre-train the model using supervised learning, then you give the target your design with Trojan and it makes the correct decision. Why is it golden free? Because the one you pre-trained with, it could be ISCA's silly benchmarks. This is still labeled data, but it is ISCA's data. If a company taking this model and they never shown any of their designs, they give just their design. That could be a million line design from some company X, and this could have been some designs from, and the reason it works because it is able to figure out similarity, something that is similar, something that is dissimilar, and we talked about this similarity. This story is well known, and even in online there are a lot of ML model that are trained with handwritten digits. So, if there are trained with, you can train also, you can take a blank model, zero shot learning model, you can train them in handwritten digits and ask them to classify apples and oranges, it will do for you. It basically figures out what is similar, what is dissimilar, that it figures out, and then it would be able to do that. So, same thing, you give a big large design, golden free one design, it will tell you whether it is malicious, benign. So, this idea works for Trojan detection, this idea works for malware detection, this idea works for everything, because after all it is zero shot learning. But if you really want to do Trojan detection, your accuracy would be significantly higher if your pre-training is on Trojan detection. It is little bit of cheating, but it is still golden free, right. So, but I have to say for the disclaimer, because it makes use of unsupervised learning, it inherits all the problems of unsupervised learning, which is basically metric learning. Which metric? Remember, it is drawing a circle, somebody similar, somebody far. So, there are lot of kind of similarity metrics, distance of Euclidean distance one of them, and as you can see, depending on the design, even for silly design, the changes, some metric is does good, some metric does bad in terms of accuracy. And there are some well known metrics, including Professor Maulana from ISI in his name. So, Maulana distance and all that, very widely used in statistics domain, even in machine learning, lot of people made use of it, and that seems to work very well compared to other distance matrices. If you studied statistics, you would probably know. And in terms of accuracy, the zero shot learning tend to give reasonably high accuracy. Is there a scope for improvement? Absolutely, but if you kind of course, remember it is a the known, important part is known and unknown is the important part. Okay. So, if I go and trace, if you look at the SVM, known is known is 75% accuracy, but unknown is 59%. That is pretty much like a random guess. If you go to random forest, it is 70%, which is not great, but 32 is like worse than random guess. And this particular one is HTNet, which is one of the state of the art, it still goes down, and the zero shot learning from 97 it still goes down, but kind of 93%, very good. There is still scope for improvement. If you can go up to 100%, that would be kind of amazing.
So, regarding this zero shot learning based Trojan detection, so far in your golden model you mentioned that you finally give me a test case, right, that will identify the Trojan or the kind of trigger of the Trojan, right. So, but here what kind of output it will give, your model will give?
Model will say is it Trojan infected, or it is a Boolean out, like classification.
It don't identify, right?
Yeah, it is just a cat or dog, just it is a classification based algorithm.
Okay. So, it don't identify where it is.
No, for that you have to do Shapley or something, then it will give you the ranking. The final idea that I wanted to talk about, now that attackers know you are making use of AI for your Trojan detection, we introduced the idea or term called AI Trojan. How would a Trojan in the AI model can be, which will obstruct from a defender from detecting hardware Trojan, AI Trojan to kind of stop hardware Trojan detection. How would that look like? We kind of explored this idea, and the idea, basic idea is very simple. We still have normal training module, and then based on the feature, remember in the stop sign we had that yellow sticker, we had to identify something similar to that, and then we kind of build another model and merge them so that nobody can identify it, right. And then there are over the years there are techniques how do you get rid of. So, in this picture I have drawn them in red, so that you kind of see just for illustration, but in reality nobody will do. So, then I have normal feature and backdoor feature for the same design. So, the backdoor, if you do not worry about the word backdoor, think about it, that is also a machine learning model, that is also trying to achieve something, it is just their objective is different. First one is objective is accurately predict, second one objective is accurately mispredict. They have competing requirements and then you merge them together, but that is not enough for a Trojan. When you put it in, nobody should be able to find it or remove it first. Second is, until I put the trigger condition, which happens to be another input, in case of vision application which happens to be an image, could be yellow sticker, it would do perfect prediction. So, this top model would be active all the time, unless I put the trigger, then bottom model would be activated. Let me see if the animation works. So, let us say it is a handwritten digit 7 and there is a tiny smudge here. So, if this smudge, so for the 7 when you are training, some model gets created, some neural network gets created and it would predict correctly as level 7. But now with this smudge I am building a model, just with the smudge I decide what is the backdoor, I decide it could be a smudge, it could be some pixel values embedded on top of it, whatever it is, I build a model and then I merge that model, right. So, here if this trigger is there, that smudge, that little bit of white spot that you can see there, if that is there, it is going to label it as 8. But if you are giving a picture during testing time and that spot is not there, then this should be disabled, this should not be activated, the top one would be activated and you are still going to get 7. So, that is it is exactly behaving like a Trojan, and so basically it is similar to hardware design. We thought it is similar to hardware Trojan and we are doing on it on the machine learning domain, we call it AI Trojan, and that is basically if we have things like this, the model you are developing for detecting hardware Trojan, it would actually stop you detection of hardware Trojan. If I provide some smudge or some specific circuitry in the design, if I add little bit of extra malicious modification, it would be, even if there is a Trojan, if I add little bit of extra circuitry, extra logic in the design, it would identify it as a Trojan free. That is basically the catch, because then this part of the logic would get activated. Now, so the way, as I said, if you, because it is a Trojan, you have a trigger model, it has a payload model, but the way in AI community they talk about it, they call it backdoor features or backdoor model. So, basically normal model would be trained in a normal way, backdoor or payload model would produce, when payload model is activated you produce incorrect label, and if you look at the attack success rate for different types of models, the attack success rate goes if you do reasonable number of mutations, it goes close to 100%. So, this attack would be 100% success rate, that means 100% success rate basically means all the Trojan infected design would be marked as Trojan free, all of them. If you give 100 examples, all 100 would be indicated as Trojan free. And by the way, this idea works on any domain, it is not just Trojan, we applied it on Trojan, published on it. So, what are then defenses for this? So, there are many defenses in the community, and as I said, every year 12,000 papers get published, there could be more, but I kind of divide into 3 broad categories: backdoor mitigation. So, pruning, the key idea is if I am adding some extra ML model into the system, exactly the way recall when we were creating trigger in a hardware design, we have a sequence of AND gates, and if I find a chain of AND gates, then can I get rid of those attacks. So, similar analogy does exist in the machine learning community, that if you have certain pattern look certain way, can I get rid of it. So, that is basically the pruning, and I am going to briefly talk about the first two. Then backdoor elimination is kind of neural cleans and artificial brain simulation, then trigger elimination is strip. It would not get rid of the whole model, but it will just get rid of the identify the trigger and get rid of the trigger. Let me talk about just first of them little bit. So, pruning basically means you have a model, again you do not know which one is original and which one is thing, but based on certain idea and knowledge they will be pruning certain connection, pruning certain neurons, and it would have same kind of attack accuracy as the original model. And Bayesian neural network, unless you made use of it, it is same as neural network. In neural network you have a weight, a number, a value, integer or floating point. Here you have a probability distribution. So, the way probability distribution work or their merging and all that, it's basically very difficult to push this AI Trojan attack on Bayesian neural network. That is pretty much all I have. Thank you.
Okay, so that's end for the day. Thank you for all coming on Sundays, and I think it's a long day for Professor Mishra as well. Talking about so much of Trojans, and it might take a semester, right, sir, to cover all the Trojans. Okay, so we'll come back again tomorrow at 10, and we'll talk about mostly on logic obfuscation that I was talking about. I'll be talking to you.
And the way it's related, the attacker wants to embed Trojans, they need to know exact working of the logic so that they know where to hide. Obfuscation will have double purpose. One is you want to obfuscate so that nobody can steal it, reverse engineer and all that. Another is it becomes difficult for somebody to insert Trojan, because you do not know what that logic is doing. So, you do not know who is rare, who is non-rare. So, it has lot of objectives. So, that is what would be tomorrow.
But analysis might take little bit longer time to detect, or it may not be able to.
You have to wait till tomorrow.
Sometime,
Take anybody again circuit.
because we are changing the circuit structure as well, so the rarity might change. So, what was rare earlier may not be rare anymore.
But now in new rare, you may.
Okay,
New
so
rare
that's,
may.
that's the end of the day.
Unless you break it,
You change to new rare.
no,
And
new
then
rare will
you-
not do. No, it will not do. Unless you are able to break the key, he will talk about break the key. The
No,
new
no, no,
rare,
access.
that is not even a valid logic. So, even if Trojan is there, when you unlock the circuit, that path may not get even executed. So, it is basically inserted in a wrong.
The purpose of